Hello, today I would like to tell you something about the basics of MR spectroscopy or MRS with a focus on spectral editing. NMR is based on magnetization that originates from a large collection of nuclear spins. Now, for the purpose of this talk, nuclear spin is just assumed to be an intrinsic property of certain atoms, and it basically, you can see nuclear spin as behaving like a small bar magnet. Now, if you then look into the human brain, the protons inside water all have nuclear spins. And if the subject is in an external magnetic field, then you will see that all of these little bar magnets that are represented by an arrow are essentially randomized for the far majority of them. Because they have a random orientation, if you add them all together, you get no macroscopic signal. But because the magnetic field is there is a small amount of nuclear spins that are biased in an orientation that is parallel to the B0 field. That is energetically more favorable, and so a small fraction of the spins are in this energetically more favorable orientation. And if you now add those spins together, you can get a net macroscopic magnetization factor M0, which represents your NMR signal. But it is never detected along the so-called z-axis parallel to B0. What we do in NMR is we rotate the magnetization by 90 degrees. And the way to do that is to apply a secondary magnetic field, B1, that rotates at the same frequency as the nuclear spins. Because the angle between B1 and M0 is always constant, the magnetization experiences a coherent torque and is rotated towards the transverse plane. Once the magnetization is in the transverse plane, the secondary magnetic field B1 is turned off and the magnetization rotates in the XY plane while it decreases because of T2 relaxation. Rotating magnetization can induce a voltage in a receiver coil, and that induced voltage represents the NMR signal that we deal with every day. Now you can see that the magnetization is rotating at a certain frequency, and at a very practical level, NMR is really concerned with the detection and separation of different frequencies. And that all has to do with the Larmor equation. The Larmor equation relates the frequency of the nuclear spins in megahertz to the external magnetic field B in Tesla. For example, if we're at a magnetic field of 7 Tesla, then for protons the Larmor frequency is around 300 megahertz. And that is because of this scaling factor. That is a nucleus-specific constant expressed in megahertz per Tesla. If we now look at protons, that constant, gamma, is about 42 megahertz per Tesla. So as I said before, if we're at a magnetic field of 7 Tesla, then the Larmor frequency is around 300 megahertz for protons. At the same magnetic field, phosphorus atoms resonate at about 120 MHz. Sodium at 79 MHz, carbon-13 at 75 MHz, and deuterium at 46 MHz. Now, if NMR was only getting signals from all the protons at 300 MHz and all the phosphorus at 120 MHz, it would be not very interesting. Fortunately, there is a secondary effect. If we zoom in on the frequency area around the Larmor frequency for protons and we detect the signal, in this case from human brain, you can see that in that very narrow frequency span around the Larmor frequency, there is a wide range of frequencies that we can detect. Similarly, around the phosphorus, not all phosphorus atoms resonate at exactly the same frequency. There is a bit of a spread. And that the same is true pretty much for every nucleus on this slide. Now, what is this caused by? What is this frequency variation caused by? Well, it has to do with electronic shielding. So here we have a proton, dus an isolated proton, and if we place it in an external magnetic field B0, then the magnetic field experienced by the nucleus is exactly the same as the B0 field. And then according to the Larmor frequency, that gives us a certain Larmor frequency. Now, of course, we never have just an isolated nucleus. There will always be a cloud of electrons around it. These electrons generate a secondary magnetic field, a so-called shielding effective field, that opposes the B0 field. And so in this case, the field that the nucleus experiences is slightly lower than the external B0 field. If the field of the nucleus is slightly lower, then the Larmor frequency also has to be slightly lower. And so you can see the horizontal axis, you can read that as the frequency at the nucleus, left being higher frequencies. Then you can also see that the electronic shielding is better on the right side. Now, of course, a proton surrounded by an electron cloud, it doesn't really happen either. Typically that proton is part of a larger molecule. Depending on the other atoms, the proton may have more or less electron density. In this case, it will have a less electron density. The shielding is therefore worse. The frequency at the magnetic field at the nucleus is therefore higher, and therefore the resonance frequency is higher. And so you can see that the exact position of the resonance frequency is extremely sensitive to the chemical environment of the proton. And this gives a lot of chemical information. The NMR spectrum, the frequency, gives you a lot of information about the chemical environment of a given nucleus. So the way the Larmor equation should be read is that the frequency that you observe is proportional to a constant times the magnetic field at the nucleus. So that is of course primarily B0, but there is a little bit of a shielding effect in there as well. Now if we now look at lactate, lactate has a number of protons that can be detected with NMR. Typically the ones in the OH and the COOH, those are exchanging with water, and those are not readily observable. But the one in blue and the three in red are observable, and it gives you a spectrum like this, in which the single proton here has worse electronic shielding and therefore a higher frequency, and the three together here are at a lower frequency because the shielding, the electronic shielding, is better. Now this is at a magnetic field of 3 Tesla. They are resonating at about 127 megahertz, plus or minus a little bit. If we now go to 7 Tesla, we basically get the exact same spectrum, but the resonant frequencies are different. So this is quite inconvenient, right? If two persons that have different magnetic fields talk to each other, they basically talk about very different numbers, even though they talk about the same molecule. Now, what you now can note is that the frequency difference between this resonance and this resonance is 357 Hertz. At 3 Tesla, the Larmor frequency is 127 megahertz. So 1 part per million is 127 Hertz. Therefore, the 357 Hertz can also be expressed as 2.8 ppm. At 7 Tesla, the frequency difference between the two resonances in Hertz is much larger. However, the ppm is also large, and therefore if we express the frequency difference in ppm, we also get 2.8 ppm. So it is very convenient to express frequencies in parts per million, because then we're talking about the same number at different magnetic fields. The only thing that is remaining is, where do we define 0 ppm? Typically a special molecule such as this is chosen, which has very, very good electronic shielding of the protons, and therefore it gives you one of the lowest frequencies possible. That low frequency is defined as 0 ppm, and then based on the frequency differences, this resonance then always resonates at 1.3 ppm, and this resonance always resonates at 4.1 ppm. So the chemical shift in ppm is just another frequency axis that is essentially normalized, so that numbers are the same at different magnetic fields. So now let's have a look at a proton frequency for a human or animal brain. This is a proton spectrum. It has like the typical resonances, but because there are so many signals in this spectrum, spectral overlap is very common. For example, if we look here, we have the creatine signal and the GABA signal as well. It is not very easy to look at the GABA because the creatine is very much larger. Similarly, that resonance is actually the sum of creatine and phosphocreatine that resonate very close to each other, making it very difficult to separate them. In another part of the spectrum, you have glutamate and glutamine. They are partially overlapping on the 4 position. In the 3 position, they overlap much more. And then in addition, underneath this spectrum, there is basically a macromolecule like contribution that makes it basically overlap with almost all of the metabolite signals. Now, spectral overlap is not a specific problem for proton NMR. You can find similar problems in, for example, phosphorus NMR. If we look at this part of the spectrum, this signal over here is the sum of ATP, NAD+, NADH, and UDPG. And so spectral overlap is common to most forms of NMR. So then the question is, what can you do about it? Let's say that we want to observe GABA. Well, because of the large creatine signal, it is not very easy to observe GABA directly. So one thing you can do is try to go to higher magnetic fields. This is the spectrum, simulated spectrum from glutamate and glutamine, and you can see at a low magnetic field, they basically overlap at all of the positions in the spectrum. If you now go to higher and higher and higher and higher frequency, then you can see that especially at the 4 position, the glutamate here, in blue and the glutamine in red are nicely separating out. And so therefore at 500 megahertz, it is very simple to just separate them based on the chemical shift alone, which would not be possible at very low magnetic field. Now, this is of course a very expensive solution because it's very expensive to buy a 500 megahertz MR system, but also it doesn't really help for some forms of overlap. For example, creatine and GABA, they are still overlapping even at 500 megahertz. Another way that you could try to separate signals is to use differences in T2 relaxation. Here are some relaxation curves for NAA and creatine and also for macromolecules. And you can see macromolecules have a much shorter T2. That means that if you acquire a spectrum at a short echo time, you get everything on top of each other. But if you acquire an echo time that's a little bit longer, the macromolecules have decayed to 0, and you can see that you have a very flat horizontal baseline. And so that you can definitely observe the metabolites separated from the macromolecules. The difference in T2 between metabolites is relatively small, and so this is not a good way to separate individual metabolites. Similarly, you can use differences in T1 relaxation. You invert all of the magnetization and then let it recover. Macromolecules have a short T1, so they recover fast. And if you excite magnetization at this point in time, the macromolecules are zeroed out, and you get a signal from metabolites only. If you excite magnetization at this point in time, then the macromolecules have nicely recovered and the metabolites go through 0, and you have a macromolecule only spectrum. Differences in T1 between metabolites is again too little, and so you cannot separate different metabolites from each other by this method. The best way to separate different metabolites is based on scalar coupling. Now, what we have to know is some of the interactions between different nuclear spins. Here we have a nuclear spin that gives a certain frequency, and here is another nuclear spin with another frequency. They of course tumble, and so basically they experience each other's magnetic fields because the nuclear spin just generates its own magnetic field, but it is randomized. And this kind of random through space interaction leads to T1 and T2 relaxation. So a spectrum of this system will give you 2 signals in which there is some line broadening because of T2 relaxation. Now there are also non-random interactions that go through the electrons in a chemical bond. So now the red and the blue spin are inside the same molecule and they are connected through each other through a chemical bond. In this scenario, the blue spin can detect if the red spin is parallel or anti-parallel to the magnetic field. If the red spin is parallel, the frequency is slightly lower for the blue spin than if the red spin is anti-parallel, then the frequency is slightly higher. Now this is a so-called coherent true bond interaction, and that leads to scalar coupling in the sense that the single resonance frequency that we had here splits into 2, separated by the scalar coupling or J coupling constant. Now this resonance is referred to as a doublet resonance. This is a singlet resonance, and this is now splitting into 2 resonances referred to as a doublet. If there is one doublet in the spectrum, then there must be somewhere else another doublet or triplet or quartet signal. Because if one spin interacts with the other, then the other interacts with the first. And so there always has to be 2 doublets in a spectrum if you have one of them. Now how can we utilize this effect to separate different metabolites from each other? Well, you need two ingredients. You need a non-selective spin echo and a selective spin echo. So spin echo is basically a 90-degree delay, 180-degree delay, and then acquire your signal. If you look at molecules that don't have scalar coupling, like water or NAA, the spin echo basically refocuses magnetic field inhomogeneity, but at the end, at the top of the echo, the magnetization is nicely along the y-axis. And if you increase your echo time, this is basically longer and longer and longer echo times, the signal decreases because of T2 relaxation, but the signal is always up and positive. There is no modulation there. For scalar coupled spin systems, during the echo time, the phase evolution because of scalar coupling is not refocused. And therefore, at the top of the echo, there is a net phase difference between the two signals in a doublet. And so you can see here at zero echo time, both signals in a doublet are up and positive, but then when you increase the echo time, you can see that you get a modulation of your signal. And so important echo times are 1 over 2j and 1 over j, especially 1 over j is going to be important later on, because you have a scenario where the doublet is inverted relative to the signal from non-coupled spin systems. Now this is one ingredient. The other ingredient is basically the same NMR sequence, the same echo time, but then the 180-degree pulse is selective for only one of the two doublets, one of the two scalar coupling partners. For uncoupled spins, nothing changes and you still get the exact same behavior. For scalar coupled spins, the phase evolution that is associated with scalar coupling is now going to be refocused. And that means if you now increase the echo time, you can see that the modulation that we saw on the previous slide is no longer there. The signal stays up and positive all the time. Now this can be utilized with a so-called J-different editing sequence. This is again a regular spin echo. If those selective 180-degree pulses are turned off, is basically a non-selective spin echo. If the 180-degree pulses are turned on, it becomes a selective sequence. This is the spin system under investigation. We are interested in observing the gray doublet associated with spins I, and they have a scalar coupling with spins S. Both signals are overlapping. This one is overlapping with lipids, and this one is overlapping with water, so they cannot be observed directly. If we now run this sequence, first the non-selective spin echo, you get this spectrum, in which the non-coupled spins are all up and positive, and the I spin is negative. The S spin is lost because of water suppression. If we now do the selective spin echo, in which the selective pulses are now selectively refocusing the S spin, but not the I spin, then we're having a inhibition of scalar coupling evolution, and our I spin is up and positive. All the other resonances are identical between the two spectra. So if we now subtract the two from each other, we're going to get an edited difference spectrum in which we only see the edited I spin. The advantage of J-difference editing is because you store these two data sets separately, you can also add them together, and that gives you all the other signals. So this is the principle of J-difference editing. Do two experiments, one with and one without J evolution, and then the difference will give you your edited signal. Now this is a very theoretical sequence. For a more practical implementation, you need to have spatial localization and water suppression, and so the megapress is one of the earlier very practical sequences to achieve this in vivo. You see it's the double spin echo associated with press, and then there are the selective 180-degree pulses to achieve the editing. More recently, people have also started to use Mega S laser. The principle is exactly the same, except the spatial localization is now based on semi-laser. Now let's have a look at a practical example. We want to observe GABA through J-difference editing. This is again our total proton spectrum, and we know that GABA resonates at these three positions. It basically overlaps, the 2 position overlaps with glutamate, and the 4 position overlaps with creatine. The 3 position overlaps with mostly the NAA. Now, the first question is, which GABA are we going to observe? Well, the typical choice is to observe GABA H4, and that is because to a first approximation the GABA H4 overlaps only with creatine. Creatine does not have scalar coupling, GABA does, and therefore you can expect an absolute separation between creatine and GABA. If GABA H4 is the one to be observed, then its immediate scalar coupling partner is the GABA H3. So the editing pulses are going to be applied at the H3 position in order to selectively observe the 4 position. So this is the experiment. Here the selective 180 degree pulse is at the GABA H3, and if you look at the GABA underneath, theoretically it is a triplet signal, but it is all up and positive because of the selective spin echo. If you then do a non-selective spin echo, so the selective 180 degree pulse is not applied here, then the GABA underneath here has a phase evolution and the outer 2 resonances are inverted. And therefore that means if you subtract the 2 experiments from each other, you are going to get the outer 2 resonances as shown here. There's also some co-editing from glutamate because the editing pulse isn't selective enough, and you also touch the glutamate H3, editing out the glutamate H2. That is not really a big deal because it doesn't overlap with GABA. Similarly, the editing pulse touches the NAA signal here, and therefore in a different spectrum you're going to get a negative NAA signal. Is also not a problem because it doesn't overlap with GABA. If you repeat this experiment, you can see that you can get very reproducible results. We should look a little bit more at this co-editing. As I already mentioned, the glutamate isn't really a problem, but there is a form of co-editing that is a problem. So again, this is the GABA, GABA H4, GABA H2, GABA H3. And we also need to look at the macromolecules. This is a typical macromolecule spectrum with about 9 distinct resonances. For GABA, we need to apply the editing pulse there. And the editing pulse, of course, has a finite bandwidth. And by putting the editing pulse there, we basically edit out the GABA H4. Now, unfortunately, macromolecules also have scalar coupling between macromolecule number 4 and macromolecule number 7. Now, if the editing pulse is narrow-banded enough so that the M4 isn't affected, then everything is good. Unfortunately, M4 and GABA H3 are so close to each other at lower magnetic field that it is impossible to make this pulse narrow-banded enough. Therefore, you touch M4 and therefore you partially edit out M7 as well. Therefore, the edited GABA at lower magnetic fields, 3 Tesla and lower, the edited GABA really is the sum of GABA plus some fraction of the macromolecules. And this is typically referred to as GABA plus to indicate that it is GABA, but there is also more underneath the edited signal. So this just needs to be, you need to be aware of this. Other practical considerations relate to temporal instabilities. Normally we're editing for relatively low concentration metabolites and we need to average for quite a long time, let's say 25 minutes. Now we need to do 2 experiments, a non-selective experiment and a selective experiment. You can do it like this, 12.5 minutes of one, 12.5 minutes of the other. But that is the bad way of doing it. The better way would be to do it very fast, let's say 30 seconds of one, 30 seconds of the other, 30 seconds then, etc., etc. The reason that the second one is better is because no system, and especially in vivo systems, are perfectly stable. For example, on this particular magnet there was a frequency drift. The magnet is not perfectly stable and there's a drift in frequency. At this point in time the subject had to sneeze, leading to bad data. Now if you acquire it according to the second scheme, you can basically remove this bad data and you can do a frequency alignment to get rid of the frequency drift. That would not be possible with the first acquisition scheme. So if you would do the first acquisition scheme, actually the data looks pretty good. Right? This is the total spectrum, this is the GABA edited spectrum. Superficially it looks quite good. But if you look at more detail, there is definitely a subtraction artifact there of the choline, and you can even see a subtraction artifact for the creatine. And that is because the frequency drift makes it that the subtraction isn't perfectly clean. If you now do the second acquisition scheme, you do the frequency alignment, you can see that first the peaks are much narrower because the line broadening caused by the frequency drift is removed, so your SNR improves, and then the difference is also cleaner. There is no subtraction artifact, and the edited GABA is much cleaner. Finally, we've been talking about GABA because that is a very popular molecule to observe. But of course, once you have the editing sequence established, you only have to change two things to edit for other molecules. Let's say that you're interested in lactate. Well, all you basically need to do is to change the echo time and change the frequency of the selective pulses. And so here we have the total spectrum, and then by editing for lactate, you can see you can get a very clean edited lactate signal. Let's say that you're interested in 2-hydroxyglutarate. Again, you only have to change the echo time to be optimal for this molecule, change the editing frequency offset, and you can basically edit for 2-HG. Now, for certain molecules, you can also achieve the editing of different molecules at the same time. Hermes and Hercules are different editing techniques that allow you to edit, for example, for lactate and 2-HG within the same acquisition, so not losing any time. Instead of doing sequential lactate editing and then 2-HG editing, they can be edited in the same experiment. So in summary, I hope I've been able to show you that spectral editing based on scalar coupling is a very powerful method to reduce or even eliminate spectral overlap for specific metabolites. Creatine and GABA is a good example. Lipids and lactate is another one. J-difference editing is the most popular method because it's relatively easy to implement. You can get your editing target, GABA, but also the overlapping compounds like creatine, and so you get everything. Other forms of editing, like multiple quantum-based editing, can also be very, very good, but you can only get the edited signal. All the other signals are destroyed within the experiment, so you would have to do a second experiment to get those. Co-editing is definitely the rule, not the exception. For GABA, it is macromolecules that are an issue. For other editing targets, you have to establish what other molecules can potentially be edited out as well at the same time. And finally, spectral editing can be very robust. However, in vivo MR measurement and especially spectroscopy measurements are very sensitive for a wide range of imperfections like frequency drift, motion, shimming, and so you always have to be aware of these kind of imperfections. Finally, if you enjoyed this video, I also have a YouTube channel. You can look for basics of in vivo NMR. At the moment there's about like 10 videos on these subjects, and I'm going to be adding a lot more in the near future. And a lot of what I discussed today can be found in this third edition of the In Vivo NMR Spectroscopy book. With that, I would like to thank you for your attention.
My name is Ashley Harris, and thank you for joining this educational lecture on the limitations and considerations for GABA data. This talk is aiming to discuss some of the practicalities of designing and analyzing GABA-edited data. So I'm going to just jump right in and do a quick refresher of how GABA-edited MRS works, or the approach known as megapress or basing editing. The GABA molecule shown here on the left gives rise to 3 resonance peaks on the proton spectrum shown on the right. These peaks exchange information by the property known as J-coupling. To measure GABA with edited MRS, we exploit this coupling property, and in particular we use the coupling between the 1.9 and the 3 ppm resonance peaks. So in the typical spectrum, we see that there are many different peaks, and GABA is there, and it does contribute to the signal. It's just that the GABA peaks are so small that they're hidden under these larger overlapping peaks. So in the edited experiment, we rely on coupling, as I mentioned on the previous slide, and we apply a frequency-selective editing pulse at 1.9 ppm, and this modulates the coupled GABA signal at 3 ppm. But this frequency-selective editing pulse doesn't affect anything that isn't coupled to 1.9 ppm, and in particular, it doesn't affect this overlapping creatine peak at 3 ppm. So just to look at those two signals, this frequency selective editing pulse will manipulate the coupled signals. So for half of the acquisitions, or half of the averages in our acquisition, we apply the editing pulse, which is known as the on subspectrum. And so our GABA at 3 ppm, the coupling refocuses and the GABA peak looks like this. In the other half of the experiment, the off subspectrum, we don't apply that editing pulse to refocus the GABA peak, and so the coupling the coupling evolves, and so the off subspectrum looks like this for GABA at 3 ppm. So when we take the difference, we're able to resolve a GABA spectrum. Creatine, as I said, isn't affected by that frequency selective editing pulse. So the on and the off subspectra look the same. So in the difference, creatine subtracts away. So combining this to look at the full spectrum, or the GABA edited experiment, as I said, in the off subspectrum, we apply this frequency selective editing pulse, which affects GABA, which is hidden under this creatine pulse. And then in the off subspectrum, we don't apply that. Creatine is the same between the on and the off subspectrum. So when we subtract the off from the ons, we subtract that creatine away and we're left with this GABA peak. And the area under this curve is proportional to its concentration. I do want to note that difference functions don't subtract away noise. They subtract away that overlapping creatine peak, but we are still left with a lot of noise in our experiment, and therefore our GABA acquisitions tend to be noise limited, so we use large voxels and long experiments, and I'll come back to this. So in this talk, I'm going to talk about macromolecules, I'm going to talk about tissue correction and frequency drift, which are some of the considerations that we need to think about. So if you'll recall, I said that the editing pulses applied at 1.9 ppm manipulate the coupled signal for GABA at 3 ppm. Unfortunately, which I'm showing in this bottom spectrum, is that we also have a macromolecular peak at 1.7 ppm that is coupled at 3 ppm. So that means we have what's known as co-editing, and co-editing is where our pulse at 1.9 ppm partially inverts or partially edits that 1.7 ppm macromolecular peak such that it is produced in the different spectrum. And so and because it's also at this macromolecule signal is also at 3 ppm, we have contamination of our GABA signal. And this contamination is pretty substantial. It's about 50% of the GABA plus signal, and that's actually where GABA plus comes from. GABA plus stands for GABA plus macromolecules. So we've got a few choices. You can just accept it, and that's what many studies have done, and they report on GABA plus, but there is an alternative, and this is known as the suppressed approach. And so, as I said, we've got this signal at 1.7 ppm that's coupled to 3 ppm. We apply our editing pulse at 1.9 ppm to affect our GABA signal at 3 ppm. Typically we would I said that we wouldn't apply an editing pulse in the off subspectrum. What we actually do is we apply it somewhere that's irrelevant on the spectrum, so it doesn't impact the signal at all. But what we can actually do is place it somewhere. And what we do in the suppressed acquisition, which is also known as the symmetrical editing approach, we apply the off editing pulse, if you will, at 1.5 ppm. So it's perfectly symmetrical about the 1.7 ppm peak. And so what the goal is that we equally invert, or we equally edit the peak in both the off and the on subspectrum, so it subtracts away in the different spectrum, or the 3 ppm macromolecular signal subtracts away because it's equal in both the on and the off subspectrum. So here I just wanted to compare these two acquisitions. In the top I have the conventional GABA plus acquisition. The on pulse is applied at 1.9 ppm and the off is applied at 7.5 ppm, which happens to be symmetric about the water peak. In the macromolecular suppressed acquisition, we still apply an editing pulse at 1.9 ppm, but this time in the off subspectrum we apply it symmetric about that peak, such that we aim to remove all of that signal in the difference. So to compare the GABA signal and the suppressed GABA data, I'm looking at two different regions in which we have both GABA plus and suppressed GABA data in 12 subjects, and this figure is showing an overlay of these 12 subjects for the occipital cortex in the top and the sensory-motor cortex in the bottom. So this data is presented on the same scale, and so it's visually apparent that our suppressed GABA data, the peak is much smaller, it's much reduced because there's not that macromolecular contamination. So what does this mean in terms of the relationship between this GABA plus data and the suppressed GABA data? So here we're looking at that across those 12 subjects, and these plots show GABA plus on the x-axis and suppressed GABA on the y-axis. And in the first plot on the left, we've pooled all the data together, and it shows a moderate correlation between suppressed GABA data and GABA plus, and it's significant. But then when we break the data down regionally in the sensory motor voxel, the relationship is there. It's just it just doesn't quite reach the threshold for significance, but it is on the same order as that seen in the pooled data. However, in the occipital voxel, that relationship is completely lost, and so even if macromolecules aren't really functionally relevant, they do change, or they are different between regions, and this level of interindividual differences also changes between regions. So overall, we find that there is a relationship between GABA plus and suppressed GABA, and it is a significant correlation, but this correlation shows regional differences, and we attribute these regional differences to interindividual differences in and this is in line with substantial interindividual differences in as reported by Terpstra et al. What it means is it really does impact how you interpret your GABA plus data. I am an advocate, I guess I would say, for suppressed data, but I do want to acknowledge that it does come with its limitations. It does have much lower signal to noise ratio because that peak is smaller. It is a little bit more difficult to do. The experiments themselves are a bit more unstable, but it comes at this benefit of having much higher specificity. So next I'm going to move along into tissue correction. So correction, and why do we care about it? Well, I'm using this clinical population, or the study of a clinical population, to really emphasize the impact of changing tissue. And this study was of primary progressive aphasia, which is a form of dementia that shows neurodegeneration in the language centers. And I've chosen this slice to be particularly compelling or provocative, that we see there's really substantial atrophy in the inferior frontal gyrus on the left-hand side of the brain, but we don't see that same level of atrophy on the right-hand side of the brain, and we don't see it in other areas of the brain either. I would argue with spectroscopy, we're not interested in characterizing this atrophy. There's much more sensitive and sophisticated tools to do this. We also don't want our measurements to be biased by this atrophy or impacted by underlying structural changes. We really want to get at those underlying concentrations in the tissue. So that's where tissue correction comes in. There are multiple aspects of tissue correction, and in the interest of time, I'm not going to go through all of them, but we do want to correct for the differences of white matter, gray matter, and CSF with their different properties, and I'm speaking about T1, T2, and proton visibility. And so I'll direct you to the Kasparovich papers and the recent consensus paper by Nier et al. And NMR Biomed to see the derivations of this tissue correction. What I really want to get at is how the differences in GABA concentration that varies between tissues impacts our measurement. And if you think about that previous slide, if you think about voxels that are on the order of 25 or 30 milliliters, you'll appreciate there's really no way to escape having a mixture of white matter and gray matter and CSF in any of these voxels. And we know that there's more GABA in gray matter compared to white matter, and we know that there's a negligible amount of GABA in CSF. What we want to do is provide information about the concentrations of metabolites in tissue. We don't want to provide information about the tissue in the voxel. And so that's where we come with this phrase of tissue correction. So what do we want to achieve with tissue correction? Well, what we really want is to adjust our measurements in some way so that they're no longer dependent on our tissue voxel segmentation, but they're independent of it, such that they're comparable. So I'm just going to work through a bit of a thought experiment here. I want you to consider 3 synthetic voxels, and the first one is a voxel that is pure white matter, and that's represented here on the top left. And so the fraction of white matter in this voxel equals 1, and the concentration of GABA measured in this voxel is equal to the concentration of GABA in white matter. In the middle, I'm showing a voxel that is pure gray matter, so the fraction of gray matter is 1, and the concentration measured in this voxel equals the concentration of GABA in gray matter. And then finally, on the right-hand side, we see a voxel that is pure CSF, where the fraction of CSF equals 1, and again, the concentration of GABA measured in this voxel is equal to the concentration of GABA in CSF, and that equals 0. So when we come back to this more representative voxel that has a combination of white matter, gray matter, and CSF as shown on the bottom, our measurement in that voxel is really a composite of each of the fraction of each tissue type and the concentration of GABA in each of those tissues. And so what we want to do is correct this in some way so we can account for variance in the fraction of these tissues across subjects, for example. So our approach to do this is to somehow normalize by tissue fraction, and there are 2 types of normalization that we're going to start off at least considering. The first is the CSF correction, and this is the most common correction that's used across the spectroscopy literature, not just for GABA. And what it does is it normalizes our measured metabolite level by the fraction of tissue in the voxel to get a corrected concentration. And so because we're looking at tissue as a whole, what we're really trying to do is get rid of that void or that null space of the CSF. What this correction implicitly assumes is that the concentration of GABA in white matter is equal to the concentration of GABA in gray matter, which I've already told you it's not. There's more GABA in gray matter compared to white matter. So an alternative is to perform what's known as the gray matter correction, and in that we know because GABA is more concentrated in gray matter, we just consider that gray matter fraction. However, this correction is actually assuming that the concentration of GABA in white matter is 0, which is also not correct. But if we look at these 2 equations, they're actually related. And they're related by the ratio of the concentration of GABA in white matter to the GABA concentration in gray matter. And I'm going to call that ratio alpha. So we can derive a more generic correction that includes this alpha factor. If alpha equals 1, we have this CSF correction, and if we set alpha equal to 0, we have this gray matter correction. And so this is aiming to account for the fact that there is a ratio of concentration of GABA in white matter and gray matter. So the next question is, well, what do we use for alpha? So we look at the literature to begin with, and looking at studies of tissue extracts, we see that there's a range of alpha values between 0.09 and 0.58 in the literature, but this isn't quite accurate because MR measurements of GABA are going to be different than what you see with the tissue extract, and in particular we've got that MM contamination issue to deal with. in vivo studies, there's also a wide range of alpha values. If you extrapolate based on the fraction of gray matter or the fraction of white matter in a voxel. And so we can extrapolate what alpha is by looking at the slope of the line, I guess, when plotting the concentration of GABA against the gray matter fraction, or GABA level against gray matter fraction. And so in the literature, we see a range. This range is from 0.14 to 0.67, so it's quite a wide range, but it averages around 0.43. We also looked at some of our data to derive an alpha value, and we had data in the same subjects across 5 different regions of the brain. So as I said, derived our alpha value, and we derived it to be, and it was derived to be 0.41. While this approach to determine alpha is widely published and used, it does have its limitation in that it assumes that the main source of variability in GABA measurements is the fraction of gray matter, and that there is no regional variability in GABA. And so this is probably an oversimplification because these different voxels cluster the way they do, but it gives us some direction as to what alpha value we should be using. So then we ran some simulations in order to figure out, well, is it better to overestimate or underestimate alpha, and what kind of range do we have? And without getting into the minutiae too much, the way these simulations were set up is that if you use the alpha correction that is equal to the underlying ratio of alpha, then the line is flat, as is shown here at the 0.5 range. But what this also shows us is that it's better to overestimate alpha, as shown by comparing the 0.7 to the alpha of 0.3. This alpha of 0.3 shows a much greater relationship between the fraction of gray matter in the voxel and the GABA concentration compared to this alpha value of 0.7. So it shows us that we should overestimate our alpha. And so given the literature and our own data suggests that alpha is around 0.45, we overestimate and recommend an alpha of 0.5. I do want to note that this correction here, as I've presented it, corrects to a voxel that is 100% gray matter. And so because it's 100% gray matter, you can compare across individuals or voxels that have different fractions, but it's maybe not completely representative. And so we propose a few alternatives. But in the interest of time, I'm not going to get into the details here. I'll direct you to my paper in JMRI, and I'm also happy to have a discussion offline with anybody who has questions about this. I do want to emphasize that it does matter how you consider this concentration difference between white matter and gray matter. And I'm going to use this study by Porges et al. That looks at healthy aging to see this. So this study recruited individuals from age 43 to 96, I believe, and collected some GABA-edited spectroscopy data. And the first thing that we see is in that voxel that we acquired, with age, we see a significant variance in our tissue fraction. We see that the fraction of CSF in that voxel increases with age, while the fraction of tissue decreases. And the tissue decrease is most predominant in white matter, although it does exist in gray matter as well. So in this study, we compared different approaches to performing tissue correction. And so we compared 3 different approaches. The first of just not doing any correction, and that's shown here in red. And we see this really significant relationship between GABA and age, which is maybe not surprising, because if we know that there's more CSF in that voxel, there's less tissue to measure GABA in, so there is less GABA with age. Then we looked at doing a CSF correction, and we still see a significant age effect. However, when we performed the alpha correction, we removed that age effect, or there is no relationship between GABA and age when you perform the alpha correction, and being that when you account for this difference in concentration between white matter and gray matter. So what I suggest is that with aging, while tissue atrophies and while there is less tissue, the GABA that remains, the GABA in the tissue that is remaining isn't decreasing. And this is actually important when you think about different interventions or how you want to consider treatments for clinical conditions, because if there is changes of GABA in the tissue, that is really different than changes in the tissue that contains the GABA. So moving along, the last concept that I'm going to present today is what's known as frequency drift. And frequency drift can come from a few places. It can come from a subject who may be lying in the scanner but partially falling asleep, and so their head is sort of drifting or moving slowly across the experiment, or it can be caused from the scanner itself. And in particular, we're worried about gradient-induced frequency drift, and this comes from, or it primarily comes from, when we run highly gradient intensive acquisitions prior to our spectroscopy. So if you're running a BOLD or an ASL or a DTI acquisition, those acquisitions are really intense on the gradients, and so they produce heat, and that heat heats the passive shim coils for one. And so then when you perform your spectroscopy experiment, that heat dissipates from those shim coils, and that causes a drift in the magnetic field across the experiment. And so what does that look like? Well, on the left-hand side here, where I'm showing data that has drift. And so you can see that the creatine peak is really blurred out. It smears right into our choline peak in both the on and the off subspectra, but it also means that this creatine peak is not perfectly aligned across the experiment. So when you take the difference, we see this really significant subtraction artifact in our GABA data. When we compare that to really well-aligned data, we have nice narrow creatine peaks, and then they align nicely, so we are able to resolve a nice smooth GABA peak with no subtraction artifact. So what can we do about frequency drift? Well, we can do what's known as retrospective frequency correction. And what we're trying to do, and what I'm trying to represent in this schematic here, is with retrospective frequency correction, we're trying to realign all of our data. So on the left-hand side, you can see that this NAA peak is drifting across the course of the experiment. After having applied frequency correction, as shown on the right-hand side here, our NAA peaks are nice and aligned. So we don't have that kind of blur of our data across the experiment, and then when we do the subtraction, we don't have any artifacts in that subtraction. There are a variety of packages that can do frequency correction. On the left-hand side, I'm showing an output from today. In the top, you can see this uncorrected data is, so what we're showing here in the top two spectra on the left-hand side is an overlap of all the spectra acquired within an acquisition, or all the averages acquired within an acquisition. And so prior to correction, we see that NAA peak, as well as creatine and choline peaks, is really kind of blurred out because each of those individual averages is offset from each other. But after we apply frequency correction, that NAA peak and the other peaks are nice and aligned and nice and narrow. And then in the bottom, you can see that after correction, our NAA peak is much narrower, it's much higher, and so we have much more confidence in that measurement. And then again, on the right-hand side, I'm showing frequency correction is used in GANET, and we see that their creatine peaks realign, and we're able to resolve GABA nicely. I do want to note that this alignment was done using the creatine and choline peaks in GANET, but GANET by default now uses a time domain spectral registration algorithm. So we can correct for frequency drift over the course of the experiment, but what we can't retrospectively correct for is changes in the editing efficiency. So I'm coming back to the spectrum that's representing the GABA peaks. When you think of drift, you can think of the editing pulse moving across the experiment. So here we see our 1.9 ppm editing pulse. When across the course of our experiment, if we have too much drift, that editing pulse drifts. And so what we can end up happening is we end up editing that peak more and not editing GABA as much. And so if we sum those two, we can actually overestimate our GABA plus measure because we're getting so much more contamination. So while we can retrospectively correct for misalignment, we do have to be careful that in the case of a lot of drift, we may not be editing GABA as efficiently anymore, and we may be editing something else. So with that, I'll make a couple final remarks and recommendations. When designing your GABA study, always think about really what your goal is and what your population is and what makes the most sense. Always look at your data. It's always useful to know what your data actually looks like and what your quality is. Are you able to resolve that GABA peak? What artifacts are there? What contamination is there? And then I can't recommend enough piloting prior to starting an experiment. You can look at your repeatability, you can look at your drift, and all of these things are going to impact the quality of the data across your experiment. With that, I welcome any questions by email, and thank you for your attention.
Welcome to an incomplete guide to MRS data analysis. In this talk, you will learn about the workflow of modern MRS data analysis, and you will get an overview about the software solutions that are available. Why did I call this an incomplete guide? Well, there are myriad ways to both acquire and analyze MRS data. We'll focus on single voxel brain MRS today. Furthermore, because there are so many different ways to analyze data, the MRS field suffers from poor reproducibility and validation. Recently, this seems to be changing as the field embraces consensus and open practices, which means there is rapid innovation, and this talk may look very different a year or two from now. Before we start, I would like to recommend resources for MRS newcomers who seek to orient themselves. As I just mentioned, the field has been very diverse in the past, and many experts performed experiments and analyses in their own way. The last 3 years have seen the publication of about a dozen expert consensus recommendation articles on practically every relevant spectroscopy issue, and these are a great way to get up to speed with the state of the art and the challenges that remain. Another initiative has been the foundation of the Committee for Code and Data Sharing, with the mission to promote collaborative research and the exchange of code and data. Disclosure, I'm a current member of that committee. We have created the MRS Hub, a centralized resource for the MRS community to provide a curated open source software and code collection, a forum as a community space to discuss and collaborate, and a collection of datasets that other people can benefit from and do exciting things with. If you find yourself looking for guidance or a particular solution to a problem, join the community and ask an expert. But now, let's get started with our rapid tour through a modern MRS data analysis workflow. MRS data analysis entails every step that happens after data are acquired. So today we'll talk about the format that raw data is exported in, we'll discuss the processing steps that we perform on the raw data before we turn the processed spectrum over to the modeling. During quantification, we take parameters that the modeling generates and convert them into meaningful units of concentration. During quality assessment, we determine whether data and modeling quality of a dataset are sufficient. And finally, we'll talk about what details of MRS studies should be reported. On the right, you'll see specific consensus papers that I recommend to beginners and that this presentation leans on substantially. If you are doing in vivo MRS experiments in humans, chances are high that your raw data comes off the scanner in one of these formats. Depending on the format, the sequence developer, the software version, and even settings on the exam card, the raw data will be in different states of rawness, meaning that some steps of pre-processing may have been performed already. It is generally recommended to choose a format and settings that allow individual transients to be saved. You should not export pre-averaged data, as it will be impossible to perform critical pre-processing steps that will improve data quality. Note that the Committee for Code and Data Sharing is currently developing a specification to use the NIfTY format for processing and exchanging data in a vendor-agnostic, unified way, which may greatly reduce friction in the future. As mentioned before, pre-processing means all steps to prepare the raw data into a signal that will be modeled. We will walk through the typical steps now. Depending on the file format, some of these may have been carried out by the scanner software before export. The first step is to load the data into a software workspace, and we'll get to software solutions later. Here we have two files, a metabolite dataset and a water reference dataset from the same acquisition with the same echo time. You see signals from different receiver channels with different amplitudes and phases. The first step is the coil combination, where these signals are added according to amplitude weighting and phased appropriately. These factors are often determined from the water reference. Once the signals from the different coils are combined, we are left with one less dimension. Now we have several signals from each transient. If you look closely, you can see that they are not perfectly on top of each other because I added a little frequency drift, so the peaks are slightly shifted between transients. Simply averaging now would make the line width larger and the SNR lower than necessary. Instead, we perform individual alignment of transients, and there are several tools and algorithms to do that. Watch the signals closely. See, the alignment has been improved and the signals are much more on top of each other. The next operation is simply to average, reducing the dimensionality of the dataset further so that we only have one spectrum per acquisition left. This already looks like a fairly decent spectrum, but besides the residual water peak in the metabolite spectrum, I have just added a little artifact that we see frequently, an eddy current artifact. That is the little asymmetry in the line shape. You can see it in the water signal, but it equally affects the metabolite spectrum, and it results from eddy currents induced by switching on gradients during localization. The solution is simple if our metabolite and water data have been acquired under the exact same conditions. It is an operation called the eddy current correction, essentially a nonlinear phase correction based on the water signal. Now, watch the water signal. The asymmetry is gone and the water peak is now symmetric. The same thing has happened in the metabolite spectrum where the peaks are free from distortion. So what's left? Well, there's a big negative residual water peak in there. It's not completely terrible, but if it were any larger or ill-phased, it may mess with our modeling process, so it's best to get rid of it by applying a residual water filter. Watch what happens. Now, this looks like an actual high-quality spectrum, and that means that we're almost done. Sometimes at this point the spectrum is ill-phased, usually when the residual water peak has an odd line shape. This isn't the case here, but sometimes the spectrum looks like the red one here. And applying a phase correction means changing the phase of the spectrum such that the peaks are largely of the absorption line shape type, meaning more or less that they point up. And that's it. Unless you're doing spectral editing, because then this is where some additional alignment happens and the different spectrum is calculated. But otherwise, these two spectra can now be passed on to the modeling. And modeling means extracting quantitative estimates of signal amplitudes from the data. There are largely three ways of doing it. The first is linear combination modeling. So we let the model figure out how it can put together the spectrum as a linear combination of so-called basis functions for each metabolite. And we can accurately use quantum mechanical simulations to predict what the spectrum will look like for a given pulse sequence. The model also contains terms to account for line shape and phase shifts and so on. Sounds easy in theory, but is really hard to do because it turns out there's a lot of things that make this process difficult. Most notably, there are broad and poorly characterized signals from macromolecules and lipids under these sharp peaks. So it's a difficult problem to solve, but there are many algorithms and software tools that do it, it is generally, according to consensus, the recommended way of analyzing data for most applications. One quite popular alternative is called peak fitting, and here the algorithm doesn't use simulated basis sets but fits the data with a series of single peaks. And these can be constrained to each other by inserting prior knowledge about chemical shifts and amplitudes and phase and line shape, and in the end this often resembles basis functions for particular metabolites. But this approach is tricky when many signals are involved and when they overlap, and it is therefore rather recommended for data with fewer peaks and little overlap, such as long echo time spectra, spectral editing, or phosphorus and carbon spectra. Finally, an easy way is to just do peak integration, summing up data points or integrating a model curve to the data, and this works because the area under the curve is proportional to the amplitude. But it doesn't really work well if there is overlap, so it is only really used for very sparse data, for example in the GANET software, which is specialized on spectral editing. As I just mentioned, macromolecule signals are broad signals underlying the sharp metabolite peaks, and they should be included in the model in one of two ways. Either as a basis function derived from a measured macromolecule spectrum, which should roughly match the sequence and the echo time, but these are difficult to measure and not commonly shared, so consensus recommendation is that these are made publicly available in the future. Your best bet at this point is to check the MRS hub. Until then, the MM signals can be modeled with parametrized signals. These parameterizations are included in many software tools, but the definitions will be somewhat empirical. They may be inadequate for a given echo time or sequence, but this is all part of current research, so hopefully this is going to be addressed in the future. Now for quantification. That means taking parameters from the modeling process and turning them into something resembling concentrations. For that, we need the model parameters. Here, these are amplitudes from glutamate and creatine and phosphocreatine. And we need the relative volume fraction that gray matter, white matter, and CSF occupy within our MRS voxel. That is usually done by interfacing MRS software with tools like SPM or FSL. So why do we need that? Because there are essentially two recommended ways of reporting metabolite levels. First, by scaling them against the internal signal from total creatine, and second, by scaling them against the water reference signal, but different tissue types will have different water content and different water relaxation, so by knowing how much gray matter, white matter, and CSF are in the voxel, we can apply appropriate corrections using literature values. My recommendation is to report both whenever you can. If you see a strong effect in your metabolite regardless of the reference compound, that is good evidence that the effect is real and not just an effect of the reference signal changing. Quality assessment. How can you tell whether your spectrum and your fit are good? You should visually inspect all your data. Cortical voxels particularly can have a lot of lipid signals in them, as the one on the top, and that can interfere with modeling and should be avoided. Sometimes you see strong oscillations somewhere in the middle of the spectrum. Those are ghost signals, and they originate from outside the voxel. If they are not too big, you might get lucky, as linear combination algorithms are somewhat robust to them, but if it's this strong, this is grounds for discarding. Strong residual water peaks, as we've seen in the first bit, they may interfere with the spectrum itself, particularly if they're ill-phased, and try filtering them out. There are quantitative metrics for good spectral quality as well, and these are the signal-to-noise ratio, or SNR, which obviously the higher the better, and the line width, often given in the full width half maximum, or FWHM, which determines how well neighboring peaks are separated. Obviously here, the lower the better. You should also always look at your fits, and the main question you should ask is, does my model look like my data, and does the residual look like noise? In this case on the left, we can answer both questions with yes, this is a good fit. Here, the model fits most of the data in the left half, but there are strange things going on in the lipid region of this spectrum. The residual clearly has structure in that area, and this may be reason enough to toss this fit out. Here we do appear to have a model that fits the data, but the baseline is very contorted. This is grounds for concern at least, and rejection of this dataset is recommended. Finally, this is total failure. There are lots of unmodeled features that appear in the residual, and on top of it a very strongly bent baseline. This fit should definitely be rejected. There are metrics of modeling quality too. The first you'll hear about are Cramér-Rao lower bounds. There's a lot to say about them, so just the gist here. They are estimators of minimal uncertainty in model parameter estimation, so the lower they are, the better. CRLBs output by analysis software are often used to discard datasets above a certain threshold, but it has been shown that this is a dangerous way to introduce bias, at least when relative CRLBs are used. It's better, if you must, to use absolute CRLBs, or to use CRLBs not as a threshold, but as a weighting factor in your statistical analysis. Not all algorithms and tools return CRLBs. Alternative metrics usually involve the residual, like the standard deviation, the maximum and minimum, or the standard deviation of the residual normalized to the standard deviation of pure noise. In order to ensure reproducibility and repeatability of your results, you need to provide a lot of details about the acquisition and the analysis. Unfortunately, that hasn't always been done in the past, but fortunately, experts have just recently compiled a minimum reporting standards checklist. We won't have time to go through the details, but this is very useful to have as a checklist while writing up papers. First, you need to provide hardware details like the field strength and the type of scanner. Then, information about the acquisition, including the pulse sequence, voxel size, echo time, but also, for example, motion correction methods. Report how data are analyzed, which software is used, which analysis steps have been taken, and how quantification was performed. And finally, provide the information from your quality assessment. Importantly, show as many spectra as you reasonably can, at the very least one representative spectrum, but better, all of them. Great! Now that you know the basic MRS workflow from scanner to reporting, I will give you a quick overview of the existing software solutions that are at your disposal to perform some or all of the steps. In the last few years, a lot of new software tools for data analysis have been released, and a lot of them are now open source. Unlike the fMRI world, the MRS field was not big on open source for a long time, but as consensus emerges, new developments for processing and modeling tend to become more collaborative. So expect that even more tools are going to be released, particularly involving validation against large-scale simulated datasets and deep learning-based analysis methods. First of all, we can't really talk about MRS software without mentioning the LC model. It's widely used and widely regarded as the standard. It used to be very expensive, but 2 months ago its development was discontinued and it is now free and open source. The LC model has a very fast and robust algorithm and is very flexible, although it does cover only few of the pre-processing steps we talked about and does not offer tissue-specific quantification, so it should be embedded in an overarching workflow. Another widely used toolbox with a large user base is JMRUI, a Java-based graphical user interface including many different spectral operations and different modeling algorithms, as well as an integrated tool for simulating basis functions. It requires more user interaction, although it can be automated. There are some pre-processing steps that aren't covered, and no direct tissue correction routine is included. JMRUI is first and foremost about modeling. Tarquin emerged early as a free LC model alternative and is now well established and widely used. It includes a lot of automated pre-processing steps, it provides internally calculated basis sets, although it does not offer an interface with tissue segmentation directly. VESPA is a complete and integrated suite of tools that cover a lot of ground for spectroscopists, including a tool for pulse design, full spectral simulations, the generation of synthetic spectra, and interactive data processing and modeling. While it doesn't directly interface with tissue segmentation, you can enter volume fractions yourself. FID-A stands out here a little because it is a collection of modular tools to construct data processing pipelines, including full simulations and basis set generations. And that's the focus. FID-A does not include modeling or tissue quantification functions. GANIT is specifically developed to handle spectral editing data, such as megapress for GABA. It is completely automated, including pre-processing, peak integration, and tissue correction. Disclaimer: this is software that I have contributed to in the past and continue to support. The next 4 tools have all been released within the last 2 years and are almost complete solutions covering the entire workflow in a modular way, often encouraging users to implement their own workflows within them. Inspector covers all the bases, including fully automated processing, modeling, quantification, and visualization, and it directly interfaces with a simulation software. Osprey is similarly a modular software and built around the FID-A libraries for automated processing, modeling, quantification, and visualization. Another disclaimer: this is software I actively develop. The SPAND toolbox is a collection of modular command line tools, most notably in the R language, allowing users to build their own fully automated analysis pipelines. SPAND also covers everything from pre-processing to modeling, quantification, and visualization, and contains functions for simulations as well. And lastly, FSL MRS is another set of modular tools to build automated pipelines, again including everything including processing, modeling, quantification, and simulations. It interfaces directly with established FSL tools for visualization. Now that you have a rough overview over the field and can go out and see which of these solutions work for your preferences, let's answer one of the FAQs. Where do you get a basis set? When I was a first-year grad student, I spent an entire weekend mixing phantom solutions, filling them in little plastic bottles, and scanning them the night through. It turned out the results were unusable and I had wasted an entire weekend. Don't be like me, don't make the same mistakes. Use simulated basis sets. But where do you get them from? Well, first, ask your sequence provider. They very likely use their sequences themselves, and they may have a basis set for you, unless you are using vendor stock sequences, because vendors usually don't provide basis sets themselves. In that case, your best bet is again to search the MRS Hub. There are already basis sets there for many widely used sequences, and the good thing is that many developers use these sequences themselves, so they very likely have a basis set for these sequences already. If you can't find it, head over to the forum and ask whether someone has the basis set that you need. If you don't get help there, it's a great idea to contact the developer of your favorite software tool directly. Chances are very high that they can use their own simulation tools to generate the basis set that you need. This is a great way to develop a relationship with your software tool developer. They love feedback from you that makes their tools better, and they are usually more than happy to help you out and make your project happen. If nothing else helps, you can take on the task of simulating your basis set yourself. There are many free tools out there that can do this for you, but it is not an easy task, and you will require some expert knowledge, not just about the simulations themselves, but also about the sequence that you're using, including timings and the exact RF pulses, which are often protected information, not public, and you might not even get access to them. Simulating your own basis set is a cool thing to do, but it does require some learning. When you are using different tools to analyze your data, it is very likely that you will see different results. Different results occur as a result of different processing, modeling, and quantification routines. Even when you use the exact same pre-processing pipelines, different modeling algorithms might not agree well. These are results from a study that we conducted using more than 270 high-quality short echo time datasets that we modeled with LC Model, Osprey, and Tarquin. Even for the strongest signals in the spectrum, NAA, choline, myo-inositol, and glutamate and glutamine, we found that there can be substantial differences between different tools, both in terms of the mean estimates, but also in terms of the mutual agreement. And that means that the choice of tool itself may introduce substantial variance into your results. Dependence of results on pipelines is something that we have seen in other neuroimaging fields too. For MRS in particular, expect more research into the sources of these discrepancies and ways to improve them. And with that, we're at the end of our 25-minute excursion. Some final words before you start out on your own way. Forge a relationship with your software developer. Both of you will benefit. Be aware of new methods. The field is changing rapidly. Different analyses will have different results. Report your analysis transparently. And most importantly, ask for help. Check the MRS Hub. Thank you for your attention.
Well, welcome to this session. My name's Caroline Ray. My job today is to tell you about the neurochemistry of GABA and how it relates to bioenergetic activity in the brain so that you can better interpret it in your spectra. So today's lecture will follow the topics as explained on the screen here. First, we'll talk about excitation and inhibition. Then we'll talk about the energy budget of the brain. We'll talk about the relationship between glutamate and the bold response. Then we'll talk about inhibition and the energy budget. So how much of the energy budget is taken up by inhibitory activity. That will lead us to GABA neurochemistry, and then we'll talk about how powerful GABA actually is. So are GABA and glutamate really the yin and yang? Do they balance one another? Well, glutamate is connected to GABA by one single chemical reaction, the glutamate decarboxylase catalyzed reaction, where it removes the carbon dioxide from glutamate to make GABA. The fact that this reaction is one way and something is removed should tell you as a biochemist that this reaction is under considerable metabolic control. In other words, it's not a simple equilibrium between the two. It's a one-way reaction. And for GABA to be returned to make glutamate is quite a complicated pathway called the GABA shunt, where GABA is converted to succinate in the TCA cycle, and then it travels all the way around the TCA cycle to alpha-ketoglutarate and is converted to glutamate. So the return path is much more complicated than the synthesis path. So the two reactions are not necessarily in equilibrium with one another at all. So there is a brain energy budget, which has been calculated several times and argued over and is still being calculated and argued over. This is one example, which was made by David Atwell. And David Atwell and his collaborators calculated how much contribution to the brain energy budget is made by the inhibitory synapse. So most of the brain's reactions are taken up with housekeeping, things like changing membranes and maintaining potentials. And then some smaller fraction of it, around 43% in this case, is taken up with synaptic function. But that includes excitatory function as well as inhibitory function. And in their recent paper, Atwell et al. Calculated that inhibitory activity accounts in the cortex for less than 1% of the total energy budget. What is the relationship between glutamate and GABA? Well, let's have a look first of all at what glutamate does. It's known that there's stoichiometric coupling of brain glucose metabolism and glutamatergic neuronal activity. This important paper by Nikki Simpson and et al. Earlier on in the 1990s showed this nice relationship between the rate of glucose use and the rate of the TCA cycle. And glutamate, the amount of glutamate that's made is intimately linked to the TCA cycle. Glutamate is also known to correlate very closely with BOLD activity. So this paper shows the really nice correlation between the amount of glutamate and the BOLD signal in fMRI, showing that there's actually a really nice correlation, particularly when the brain is active, mostly when the brain is active. So what is glutamate neurochemistry? Well, alpha-ketoglutarate is a main control point in the TCA cycle, but it is linked to glutamate through a number of different reactions. The glutamate dehydrogenase reaction requires the insertion of an ammonia and is not really that important a reaction when you're talking about how much total glutamate you have. There's an awful lot of glutamate in the brain. It's in the millimolar amounts, which is quite a lot for brain. The second most, or actually probably the most abundant amino acid in the brain. All of this glutamate isn't a neurotransmitter. If it was, your brain would have blown off long ago. Actually, a lot of it is metabolic glutamate. And this glutamate participates in a number of transaminase reactions. So it donates its ammonia group to molecules like pyruvate or oxaloacetate and forms other amino acids such as alanine and aspartate. And these transaminase reactions have been calculated to be extremely important in controlling the total amount of glutamate. And the glutamate alpha-ketoglutarate pair is always the other half of the transaminase reactions. So in these transaminase reactions, the ammonia is taken from glutamate and given to another carbon backbone to form an amino acid, or vice versa. Alanine can donate an amino group to alpha-ketoglutarate and form glutamate. So it's one way that the brain keeps its ammonia levels in balance. Another way is through synthesis of glutamine, through glutamine synthetase. Now, the biochemists among you will recognize that the name synthetase implies that this reaction requires ATP. Any reaction requiring ATP is generally under fairly strict metabolic control. So the synthesis of glutamate to glutamine requiring ATP means that this reaction is strictly controlled. It's not something that is necessarily always in equilibrium. The reverse reaction, this reaction takes place only in glial cells, by the way, as glutamine synthetase is only found in glial cells. The reverse reaction, which happens mostly in neurons, but also in glial cells, is the phosphate activated glutaminase, which basically removes the amino group from glutamine and resynthesizes glutamate. So you can see that glutamate sits in the middle of a whole pile of reactions, some of which are fairly near equilibrium reactions and fairly well balanced and fast, and some which are more strictly controlled. So this brings us on to GABA. And interestingly, GABA doesn't cross the blood-brain barrier, but it doesn't stop people selling lots of GABA in bottles for you to eat. By the way, don't ever buy any of these because your brain won't absorb it. It'll all just get used up in your gut. So some useful background facts. 90% of cells and synapses in the brain are glutamatergic. That means they use glutamate. And this is one of the main reasons why glutamate levels tend to correlate very nicely with brain activity. Now, GABAergic inhibition or GABAergic activity doesn't necessarily involve sodium ions like excitatory synapses do, but changes in the chloride gradient. And the chloride ions move down a smaller electrochemical gradient at inhibitory synapses than sodium ions do at excitatory synapses. And that means that less energy is required to hyperpolarize the membrane as opposed to depolarizing it, which is what you do in an excitatory synapse. And there are different types of inhibition. 4 of them are listed here. The 2 I really would like to draw your attention to are phasic and tonic inhibition. Phasic inhibition is where GABA is released from synapses and modulates the local synaptic activity. Tonic inhibition refers to levels of GABA which generally combine with synapses which are not, with receptors which are not in the synapse, but which are extrasynaptic and which tend to control overall brain activity in the area. So if inhibitory activity only accounts for 3% or less of brain energy budget, then is it really worth worrying about? And the answer is yes, and I'll tell you why. So the devil is in the details. This is an example of a glutamatergic synapse. You can see there are a number of different receptors here. So here we have the presynaptic bouton, and here the postsynaptic neuron, and here a glial cell. So GABA is released from the presynaptic neuron, and it can react with GABA receptors in the postsynaptic neuron. That's your normal GABAergic inhibitory synapse. However, this GABA can also leak out of the synapses and react with GABA receptors which are not in the synapse. In this case, this would be presynaptic inhibition because the GABA would leak out, react with a presynaptic neuron GABA receptor, and basically make it less likely that this neuron would release GABA in the first place. The GABA could also react with a postsynaptic neuron, and that would make that synapse less likely to react when GABA is released to the postsynaptic receptor. You'll notice these other little things here, these red things, these GATs. These are GABA transporters, and their job is to remove GABA from the synapse and from the presynaptic area or the perisynaptic area, so that another neurotransmitter release will actually be released into a low GABA environment, so it would have more likelihood to be able to cause an inhibitory postsynaptic potential. However, these transporters also work backwards. So depending on what the chloride potential is on the neuron, they can actually release GABA. And if you have large amounts of GABA sitting in the synapse or sitting in the perisynaptic area, that GABA can be released when these transporters reverse. And that's one way. Another way in which tonic inhibition can take place. So GABA could be released from these transporters here and bind to GABA B receptors or GABA A receptors, which are not in the synapse. The other way that GABA can be synthesized is also through this so-called putrescine pathway here. So putrescine and other amines, biogenic amines like spermine and spermidine, can actually be used to synthesize GABA. And this takes place in the astrocyte, but it's not a huge contributor to GABA levels, but you do need to be aware of it. So with this pre and postsynaptic GABA-R activity, what do we know about this? And we did some experiments some time ago with the GABA B receptor, where we activated the GABA B receptor with agonists and we antagonized it with antagonists. Now, thinking about activating and deactivating GABA receptors you sort of have to stand on your head to understand how this is done, because activating the receptor tends to turn things off and antagonizing the receptor tends to turn things on. So what did we find when we did this? So it's interesting because excitatory and inhibitory activity together can either increase or decrease bulk brain energy metabolism. And remember, when you're doing spectroscopy, you are measuring bulk brain energy metabolism because you have a box, which is, if you're lucky, about 8 cubic centimeters. So you've got an awful lot of neurons in there. So it's bulk brain energy metabolism. So let's imagine that at resting potential, excitatory activity accounts for about 80% and inhibitory activity accounts for about 20% of total brain activity. These are figures that you actually might find somewhere in the cerebellum, which is different to the cortex. So if we put in an agonist, which basically will turn things or activate the GABA receptors and turn things off, a small amount of agonist might produce a small drop in excitatory activity, but produce a large amount of inhibitory activity. And together, you might see an increase in total brain activity. If you increase the amount of agonist, it would turn excitatory activity down even further, but not have that much more effect on inhibitory activity, and we would see a drop in brain energy metabolism. Similarly, when you apply an antagonist, which would actually turn things up, if you apply a small amount of antagonist, you would see a slight increase in excitatory activity, but a large drop in inhibitory activity, which would give you a drop in activity. And similarly, if you put more antagonist on, you'd see an even bigger increase in excitatory activity and a slightly larger decrease in inhibitory activity, which would give you an overall activation. So 118 being bigger than 100, so we would actually activate things. So the point of this is to tell you that depending on how much inhibitory activity versus excitatory activity you have, you can change brain activity either down or up. So it's all completely context dependent. GABA can also directly modulate blood flow, which in turn can have knock-ons to how active the brain can be. So this is yet another confounding factor. There's a recent really cool paper appeared just recently in Cerebral Cortex, where the authors have used a whole range of really interesting activity. But one of the things that they did was that they got some mice where they had coupled the activity of the GABA transporter to an optogenic fluorescent molecule so that they could see what happened. And they've measured the hemodynamic response function of excitatory neurons and the hemodynamic response function of inhibitory neurons separately. And what they found was the hemodynamic response function, basically the bold response that you get with excitatory neurons, is similar across different conditions. In other words, you activate it, you get an increase in activity. But the hemodynamic response function of inhibitory neurons is quite different, and it's sensitive to what you're doing and the context in which you're doing it. So it's highly sensitive to stimulus duration. If it peaks earlier than the excitatory hemodynamic response function, i.e. the bold response is initially positive and then goes negative after time. And there's also negative bold at downstream sites. So what's actually happening with blood flow and brain activity is really dependent on context in terms of inhibitory neurons and their activity. How does this work? Well, yet again, either it's through the reversal of these GABA receptors or through excess GABA at the synapse leaking out. And which there are many different GABA receptors, and their properties, in other words, how responsive they are to GABA, is really dependent on what their subunit composition is. So GABA A receptors, which contain alpha 3, 4, 5, alpha 4, 5, and 6 receptors, tend to be perisynaptic receptors. In other words, they're these tonic inhibition ones. whereas ones which are alpha 1 and 2 and contain gamma 2 subunits are more likely to be the ones that you find in the synapse. So the GABA that acts on these perisynaptic receptors is either leaking out from the synapse or being released from reversal of the GABA transporters. Well, what do we know about this and how much activity? Well, we did an experiment earlier on where we activated brain slices, and what you can see here, all you need to focus on here, not the little prints underneath, but whether the error bars, the histograms are pointing upwards or downwards. If they're pointing upwards, it means that metabolites have gone up, and if they're pointing down, it means the metabolites have gone down. And what we're looking at here is flux of carbon-13 plus total pool sizes of compounds. So if you activate slices with a compound like AMPA, which activates AMPA receptors, or EGLU, ethyl glutamate, which activates mGlu-R receptors, the metabotropic glutamate receptors, or this one, which is an antagonist at GABA-B receptors and tends to slightly activate things, you get quite a large activation. As you can see, this is percentage activation over the control condition. If you put in vigabatrin, now vigabatrin is an inhibitor of GABA transaminase, so it blocks the GABA shunt and it stops GABA being converted back into the TCA cycle. If you put vigabatrin in brains, what it does is increase the local amount of GABA, and most likely it's increasing extrasynaptic GABA. So not GABA which is found inside the synaptic boutons, but GABA which is found in the cytosol. If we have an increased level of extrasynaptic GABA because we've put vigabatrin in, and then we activate the slices with AMPA, what we find is that everything gets turned off. The same thing happens if we put ethyl glutamate in, and the same thing happens if we activate or antagonize the GABA-B receptors. Exactly the same metabolic profile, no matter how we've activated the slices. This activity is probably through altering levels of extrasynaptic GABA. And we know this because we use this molecule, TPMPA, which is an antagonist at GABA-C receptors and also extrasynaptic GABA-A receptors. And if you put that in and vigabatrin, you actually get nothing. So they cancel each other out pretty much. And this is telling us that these extrasynaptic receptors are very, very powerful. They can turn off almost any brain activity with just a tiny amount of GABA. So the point of telling you this is to tell you exactly how powerful this extrasynaptic GABA can be. So GABA uptake is regulating the cortical excitability via cell-specific tonic inhibition. So here's another paper supporting this. So in some brain areas, GABA is actually a modulator rather than a classical neurotransmitter, because the GABA can be released and it can then turn off the activity of other neurotransmitters. So it can affect the activity of dopamine receptors and other ones. So in some areas of the brain, like this one, the LSO neuron, in that case, the GABA is acting as a modulator rather than as a classical neurotransmitter. So can we actually talk about excitatory inhibitory balance? This paper from Richard Eden's group shows initially that concentrations of glutamate and glutamine and GABA were correlated across one of his large cohorts, in this case n equals 220. They then controlled for all of the lurking variables, the acquisition side, the demographics, and the data quality didn't explain the relationship. But they found if they controlled for the concentrations of N-acetyl aspartate and creatine, which they took as surrogate markers of metabolic activity, this diminished the correlation. The correlation wasn't that good to start with. It was only minus 0.4 as an R. But when you control for NAA and creatine levels, it diminished the correlation down to 0.09, R equals 0.09. So this suggests that the regional metabolism may mediate this relationship. In other words, it's context dependent. So if you're tempted to publish papers where you measure the GABA concentration and the glutamate concentration and you start talking about excitatory inhibitory balance, please don't. You may get a correlation in one place, but it's very likely that you just got lucky. So what do bulk GABA levels actually mean when we measure them in the brain? Well, they're brain region dependent, as we've seen. It depends where you're looking. They are activity dependent. So if your resting levels of GABA are quite high and your brain is activated, it is probably more likely to be then turned off when you activate it. So people with low levels of resting GABA, you might say that their capacity to do tonic inhibition is less than somebody whose levels of GABA are high in the first place. You cannot distinguish the neurotransmitter and the metabolic pools of GABA from one another. They're in reasonably fast exchange. And the metabolic pool is far larger than the neurotransmitter pool. So if you measure GABA and call it neurotransmitter GABA, you're being misleading. So GABA reflects tonic inhibition, which is the sort of tone of the brain. But as again, I said, it is activity dependent. And research is ongoing. So watch this space. New papers are coming out all the time. And thank you for your attention.
Hi, I'm Charlie Stagg and I work at the University of Oxford. And today I'd like to talk, following on from the previous speakers, to really give you some examples of how we might use MR spectroscopy to inform us about neuroscientific questions. So I'm going to talk about changes in GABA, neuroplasticity, and learning. Most of the work I'm going to talk about is in the motor and the visual cortices. Not all of it, but most of it, primarily because that's where most of the data is. But there's no sort of intrinsic reason that the kind of mechanisms I'm talking about aren't equally applicable elsewhere in the brain. So I'm going to start off really talking a little bit about why we might want to do this and why GABA in particular might be an interesting thing to look at in the context of motor learning. I'm going to talk a little bit about the studies looking at learning and reviewing the evidence for the role of GABA in learning. I'm then going to talk a little bit about perceptual learning, so moving outside motor cortex to visual system. Talking a little bit about long-term plasticity and how that, and how spectroscopy might be used to tell us about the kind of changes that are happening over weeks to months. And finally, talk about combining MR spectroscopy with non-invasive brain stimulation approaches to try and get closer to causality and try and really determine not only how do changes in GABA correlate with changes in behavior, but can we go a step further and modulate GABA specifically and look at what effect that has on behavior. And we're a long way from doing that truly causally, but it's I want to sort of show you how we're thinking and others are thinking about getting a step closer and going beyond just the correlational analyses that we're so used to with MR. So first of all, why on earth are we interested in looking at GABA at all in plasticity, right? So if I talk to a synaptic physiologist, a cellular physiologist, and say, what do you know about plasticity? They'll say, well, it's a glutamatergic process. So you wouldn't be unreasonable to think, why on earth is this something that we might want to look at in the context of GABA? And really, a lot of our thinking comes from animal literature. And this was really the study that got us and many others in the field really thinking was a study from Randy Nudo and colleagues 25 years ago now. And what they did was look at cortical mapping in the motor cortex and look at how that changed after a stroke. So the idea was they went into the monkey and they took off the skull and they did direct cortical stimulation. And at each point across the cortex, they recorded where the largest twitch was. And as you can see, there's an area that represents the shoulder, an area that represents the wrist and forearm, and an area that represents the digit. What they then did was induce a lesion in the digit representation. allow the monkeys to recover and undergo what in humans we'd call rehabilitation. So basically inducing plasticity to elicit a behavioral improvement. And when the monkeys had improved in their behavior and had plateaued, they then reopened the skull and had a look at the same areas. And whilst, of course, they didn't see any responses in the area that was lesioned, what did they say? What they did see was a massive reorganization of the other areas, such that areas that had previously innervated the shoulder now innervated the wrist and forearm and the digit. And the areas that have the parts of the body that have been trained in the rehabilitation. So we see these cortical representations really across the whole brain. And one key fact about them seems to be that the larger the representation, the more neurons are involved, and therefore the better the control of that region. And so these dramatic, dynamic reorganizations of the motor cortex are really striking. But it doesn't just happen in the context of a stroke, which is obviously a huge intervention into a monkey brain. A subsequent study from the same group showed a really substantial reorganization in rats when they were trained to do a precise grasping task, something that's not natural to them. And what they saw was, this was the mapping before they did this task, and you can see regions of the wrist and the digit. And then after they'd learnt, they saw massive reorganization such that the areas that were innervating the wrist and the digits, which were the areas that were involved in the task, hugely expanded. So this really gives us a big question, right? Which is, how on earth does a neuron that previously was innervating, the elbow and the shoulder suddenly come to control the wrist and the digit? And there are ways of thinking about that question, but one of the ways that's really compelling, for me at least, is to look at some of the physiological data. And one way that we think that this reorganization and remodeling might happen is via a decrease in local GABA, allowing glutamatergic synapses that have previously been silent to become active and undergo local glutamatergic LTP-like plasticity. And GABA is a really powerful potential mechanism for this. So this is a slice through the cat motor cortex, and what you can see in green are the pyramidal output neurons, and what you can see in red is a stain for GAD, the enzyme that produces GABA. And really what I want you to take away from this is quite how many GABAergic neurons they are and how they form this really diverse web of inhibition that's really able to very specifically and very sensitively modulate the inhibition and change the firing rates in the glutamatergic neurons to allow plasticity to occur. Is there any evidence that that might actually be what's happening? Well, yes, quite a lot. One of the most compelling studies for me is this example of a chronic in vivo recording where they took some rats and induced LTP-like plasticity here in a very standard way. And they then recorded from the postsynaptic cell. And for a given input presynaptically, in the absence of any kind of LTP, you get a fairly consistent output. If you strengthen the synapse, what you get is, for the same input, a much larger output. So classic synaptic plasticity, classic LTP-like induction. However, if you do exactly the same thing in the presence of a GABA agonist, you get absolutely no response at all. So this isn't to say that plasticity isn't a glutamatergic process, because of course it is, but rather that it relies upon a decrease in GABA for it to occur. So this then raises a number of potentially interesting hypotheses that we can go on to test with MR spectroscopy. The first of which is that if GABA levels are controlling, determining cortical representations, and cortical representations tell us something about behavior, then there should be probably a link between inhibition and behavior on a subject-by-subject basis. So that'd be a good first thing to test. And moving on from that, if we induce plasticity, so if we get healthy adults to do something that induces plasticity, like learning a motor task that critically depends on motor cortex, we should see a decrease in that inhibition as they learn it. So first of all then, can we see a relationship between local inhibition and behaviour? So we have seen this indeed. So in young healthy adults, the GABA in primary motor cortex is directly proportional to how quick you are to respond to a motor task. And we've replicated this now a couple of times. So people who have high GABA levels in motor cortex are quite slow. Motor cortex isn't as quick, doesn't work quite as well. People who have lower levels respond much more quickly. What causes that variability is something that's hugely interesting, but something that we didn't explore. And it's not just us, lots of other groups have done this. This was one of the very first studies from Cardiff back in the day, where they looked at GABA levels in the frontal eye fields and looked at distractibility, which is one of the things that is a key behavior of the frontal eye fields, and showed that people who have higher GABA also had less distractibility. So they weren't as aware or distracted by stimuli as people who had higher GABA, who were less able to be distracted, I guess. And there have been many other studies, many other regions showing this link between local inhibition and behaviour. But most behaviours in the humans aren't a single region. We are interested in complex behaviours. So how does that work? Well, there's evidence that local inhibition not only controls local behaviour, but also controls how, is related to at least, how that region connects to the rest of its functional network. A number of ways of doing this. One way of doing it is to look at resting state activity. Now we're OHBM, so I'm going to assume that everybody knows what this is. But these are subjects who we took, popped in the scanner, got them to lie at rest, and just looked at regions of the brain where the spontaneous bulb activity co-fluctuates. And you get these beautiful networks that look very much like task-related networks. So this wasn't a fancy analysis. This was a very simple network-based analysis. And we determined two networks. One, the motor network, and one, the default mode network, as a really robust, well-described control that doesn't involve primary motor cortex. So first of all, we asked the question, does inhibition within motor cortex relate to connectivity within the network? So we would hypothesize that if you have higher levels of inhibition, you have less connectivity within your behavioral network, which would be reflected in a worse behavior. That's exactly what we saw. So people who had high levels of GABA relatively had less connectivity, lower levels had high connectivity. This was specific in terms of anatomy. So the GABA in your M1 didn't tell you anything about the strength of your default mode network. And specific neurochemically, so your GLX, glutamate-glutamine, didn't tell you anything. And we replicated this in another data set in young adults and another data set in healthy older adults. And again, this is something that's been seen in other functional networks and elsewhere. So we seem to have got then a relationship where local inhibition can tell us something about behavior and can tell us something about network connectivity. So it's beginning to tell us, give us clues and hints as to how things are controlled in the healthy brain. The next question we had then, if you remember, was, okay, if decreases in GABA are important for plasticity, then if we get people to learn a motor learning task, will we see a decrease in GABA? So this was work done by James Kowasinski when he was in my lab. And what we did was take three groups of young healthy adults, one group who did a serial reaction time task with a 16 button press sequence that repeated and repeated and repeated across blocks, another group who just pressed random buttons, and a third group who watched a David Attenborough video just to keep them awake. So it was a non-movement control. And what we saw, these are behavioural results, as you would expect. As people learn the task, they get quicker at responding to the visual cues because they know what's coming next. so classic behavioral learning. But in the random task where the button presses happened in an unpredictable order, as you would hope, reaction times, response times were very, very stable. So we've got a nice behavioral effect. Can we relate that to the underlying inhibition? So there was no change, possibly a slight increase, but nothing significant in either the random or just the plain visual control conditions. But in people who learnt a sequence, GABA levels in their left motor cortex decreased during learning. And we can begin to relate this. So there is a relationship between GABA very early on in that process and the amount they end up learning that is not there with our glutamate. So I've sort of shown you a little bit about motor cortex, and I've shown you that GABA levels in motor cortex predict behavior of motor cortex, relate to connectivity of a network where motor cortex is key, and decrease with learning of a motor task. But the motor cortex, whilst being a fantastic brain area, is a bit of a weird one. It's a bit different. And so the next question really, I guess, is how much is this generalizable? Is this just some weird thing that happens in the motor system, or can we see similar things in other brain regions? So this is a study done by Zoe Courtsey and colleagues in Cambridge. And what we did was do two different tasks. So they looked at perceptual learning, and they had two stimuli. So either the dots were in a radial formation or a concentric ring. And then they added noise, either just adding noise, so signaling noise, or sort of really melding the two. So you had to pick out differences in features. And the task was you would see one of these and you would have to work out whether it was a radial or a concentric pattern. And as people do this, they get better. You get better and better at working out whether it's a concentric ring or a radial pattern. And these are our two tasks, and you can see people got better on both of them. And then the question was, can we see changes in GABA underlying these? Now, we're interested in two regions of the brain, the occipital temporal cortex and the posterior parietal cortex. And previous work from Zoe's lab had really led to some really specific hypotheses about where learning of these two tasks might occur. So if we look in the occipital temporal cortex, what we see is a slight increase in GABA there during the feature differences task, which is a task we don't think relies on this area, and it's not significant. But as people learn the signal and noise task, actually you see a significant decrease in GABA in this region. And previous work from Zoe has shown that this is really where we would expect learning of this particular task to occur. And very nicely, we looked at the posterior parietal cortex, we don't see very much at all. So we know there's no signal and noise learning going on here from her work. We might expect to see perhaps some feature differences, but actually the thing about feature differences is you want to look at maybe increasing GABA to help that. So not sure we can draw very many conclusions from the posterior parietal cortex, but our signal and noise task, which was the task that that we think is learnt in occipital temporal cortex specifically, as people learn it, they see a specific decrease in GABA in that brain region. And there's no change in glutamate as well. And we can go on. So we can look and say, well, actually, yes, not only is there a group difference, but actually there is a relationship in the signal to noise task between the amount each subject decreases their GABA in that key region and how much they learn. And actually, we see a relationship the other way for the feature differences task, which again, as you say, one might argue would be helped by increasing GABA to decrease to to increase the contrast and allow you to get better at picking out those features. So spectroscopy begins to allow us to really look at specific hypotheses about different brain regions and about what's happening within them. And we can go forward. We can ask, so this is work done by Watanabe and colleagues, and they were particularly interested in what happens during overlearning. So when you've not still actively learning a task, as I've shown you previously, but you've very, very, very much learned it, and what changes do we see in GABA levels at that point? The hypothesis being, perhaps, that you would get a decrease in GABA during learning, as I've previously shown you. So I've shown you that in a brain region we think is critically important in learning that task, we see a decrease in GABA during learning. What we know happens after that is a period of consolidation, where one might argue that GABA goes back up again, and that you get a sort of a stabilization of the strongest synapses and a weakening of the ones that haven't been necessary to learn the task. And this is really what Watanabe and colleagues were interested in. So what did they do? They looked at learning of two different tasks. And they showed that you learn your first task, and if you learn your first task, then actually that improves learning of your second task. Okay, and then an untrained task goes back again. However, if you overlearn your first task, so you're absolutely fluent with it, then actually you don't get any learning on a second task, presumably because your responses are saturated. And again, you don't get anything on the untrained task. And so what they did is look at that stabilization of memory trace and ask the question, can we see a change in GABA due to that? And this is what they saw, that when there's no overlearning, we see an increase in the EI ratio, so an increase in excitability, and a decrease in inhibition, or a decrease in inhibition, but then goes back to pretty much baseline if there's no overlearning, so there's no stabilization. But if we get stabilization of that memory trace, then actually after that learning, we get a significant decrease in EI balance, which could be interpreted as a decrease in excitation and or an increase in inhibition that then persists. So it might be that not only can we use spectroscopy to look at the mechanisms as we learn and see this decrease both in motor learning and perceptual learning, but actually as we go on and look at overlearning and look at the beginnings of synapse stabilization and consolidation of these tasks in a context where we see a behavioral evidence of stabilization and a decrease in plasticity for a subsequent task, we also see a neurophysiological evidence for synapse stabilization. So again, beginning to understand mechanisms of plasticity. Okay. So the animal literature tells us quite a lot about what we think should happen during short-term learning, so learning over minutes to hours. Okay. What it's really difficult to do in rodent models, or even really in monkey models, is look at exactly what happens electrophysiologically over weeks to months. Okay, and that's really what we're interested in, because we're not really interested in how you learn a sort of 4-button press sequence. I'm interested in how you learn a piano sonata, and that kind of plasticity happens over months. I'm not interested in recovery after stroke that lasts 10 minutes. I'm interested in how patients after a stroke can improve their behavior in a way that lasts for months or years. Okay. So I've shown you lots about short-term plasticity, and I've shown you a little bit about sort of synapse stabilization, consolidation-y type things, and the GABA changes that are accompanied by those. The next question I want to talk you through really is the question of how does GABA change during long-term plasticity? and talk you through a couple of studies that shed some interesting questions more than answers at this stage. So the first of these is coming out of Heidi Johansenberg's lab in Oxford. And what we did was look at juggling. And they took a baseline scan. They then sent people away for 6 weeks and got them to learn to juggle. And took videos and showed that people did indeed get better. They then came back, took a scan, went away, told them not to juggle for 4 weeks, and then did a final scan. And they did 2 types of training. They did either a low intensity training, where people got 15 minutes of training a day, or a high intensity training when they got 30 minutes. And you can see that the ratings, basically the higher number, the better, as to how many times you can throw a ball up without dropping them. You can see that actually the behaviour is pretty similar, depending on whether it's high or low intensity training. But actually, it's quite different in terms of the neurochemicals. So at baseline, the controls are pretty, the control subjects who didn't do any learning had a baseline and a post scan and didn't see any changes in GABA, as you would hope. Whereas subjects who did the low intensity had a GABA that decreased over 6 weeks of training, great, and then increased again as they had a rest, and had some sort of synaptic stabilization, maybe, intrinsic skill. So we see this decrease in GABA as they learn. The interesting thing, though, is that's not true of the high intensity. So a little bit of training every day leads to the pattern we might expect for long-term plasticity, but not for high intensity. So there's a real question there about what the mechanisms underlying that are, and what is happening there. We can also look at long-term plasticity in the context of stroke rehabilitation, as I say. So the recovery from stroke is an opportunity where people learn to relearn and recover motor skills over months to years. And that process is a version of long-term plasticity. And so if we think that behavior is mediated, improved behavior and plasticity is mediated by an decrease in GABA, then patients who have been through at least 6 months of recovery after a stroke should have lower GABA levels in the primary motor cortex and the affected hemisphere than age-matched healthy controls. So this was a study by Jakob Bleecher and colleagues, and what we did was exactly that. He just looked at whether there was a difference at baseline. He then went on to do some interventions, which I won't go into now for the sake of time. But what he saw was exactly that. So people who had had a stroke and have therefore had months of naturally occurring recovery and learning and plasticity had lower GABA levels in their motor cortex than age-matched healthy controls. So the final thing I'm going to then talk about is the combination of MR spectroscopy with non-invasive brain stimulation to go beyond just correlation and using, in this case, transcranial direct current stimulation, where we put a 1 or 2 milliamp current through the brain via 2 electrodes placed on the scalp. And we know that that modulates cortical excitability for a few tens of minutes. And we know that it can modulate behavior. So the first question we asked them was, does it change GABA levels? So if you're inducing this kind of increased excitability at proplastic state, do you see a decrease in GABA as you do that? And indeed we did. This was a very early study from my PhD, and what we saw is that there was a decrease in GABA within the primary motor cortex with anadal stimulation, which is something that is a proplastic intervention. And there was no change in GLX and there was no change in sham. So can we start probing then? So I've shown you before, you may remember that I showed you that GABA within primary motor cortex relates to the strength of the motor network. Can we go a step further and say, if we use TDCS to modulate GABA, can we get a change in network strength? So can we start really linking these things? We know that TDCS decreases GABA, so we would expect then, if this relationship is true, that it causes an increase in resting state connectivity. And that's exactly what we see, that motor network connectivity is increased after TDCS. I've shown you that GABA decreases in learning. Can we go a step further and try to relate that to try and probe some causality? So we can look at GABA levels in motor cortex and how much they change with anidal TDCS, so we can get a metric of GABAergic responsiveness. We can get GABA elsewhere, check that this is specific to the motor cortex, and we can get functional imaging during motor learning to look at the signature. So we've got responsiveness to stimulation on one day, so sort of GABAergic modulation, and we've got learning and fMRI study on another day. And so we can take the behavioral data from our learning study and quantify a learning measure, just as how much people decrease their response times as they learn the task. And that's very variable. But we can show that people who are very responsive to TDCS, so people who are able to decrease their GABA a lot on one day, are also those who decrease their reaction times when they're learning, so also those who learn well. People who don't have a very responsive GABAergic system really don't learn the task very well. And we can look across the whole brain and ask the question, where in the brain is there a relationship between how much you decrease your GABA in response to TDCS and how much you decrease your fMRI, your bold signal, in relation to learning? And actually, if we look across the whole brain, we see a remarkably specific relationship in the left paramotor cortex, such that this is the region where bold learning change correlates with GABA responsiveness. So that's a bit of a whistle-stop tour, and I'm very happy to discuss any of this in the questions. I hope that I've sort of given you a rationale for why we're interested in this in the first place and shown you that changes in GABA are important for plasticity and learning in humans. And that MRS, if used carefully, can tell us about human plasticity across multiple regions, domains, and timescales. And MRS combined with other imaging modalities, with behavior and non-invasive brain stimulation, can really start to unpick causality and can start to tell us about the behavioral importance and the relevance of the kind of relationships we're seeing.
Hi, everyone. Thank you very much for attending our educational session and for attending my talk. My name is Nick Putz, and I'm currently a senior lecturer at King's College London, where my lab focuses on differences in excitation-inhibition balance in children with neurodevelopmental conditions, as well as their relationships to differences in both sensory and social function. We mostly focus on children with autism, ADHD, and Tourette syndrome, but I also support the acquisition, analysis, and dissemination of MRS approaches, and I continue to do that. So today, I'll be talking about how edited MRS can be used to understand psychiatric and neurodevelopmental and neurological conditions better, and what role pharmacological approaches combined with MRS might play in this. So of course, in this short amount of time, I don't have time to go into every single drug that exists that might affect GABA or every single condition that GABA MRS has been used in. But I really hope to give an overview of the work with particular emphasis on things to think about when you're designing your own studies in clinical conditions. The goals for this talk are to understand in what disorders GABA might be altered and how these alterations might occur. Secondly, to understand how MRS of GABA can play an important role in understanding neurological and psychiatric disorders. And finally, to understand some of the limitations of MRS in terms of diagnosing disorders and development of treatments through pharmacological approaches. So we know that GABA plays a key role in healthy neurological functioning, as well as regulation of perception, which is something I work on, and cognition and other behaviors, as some of the other talks have talked about already. So in that case, you can imagine that abnormal or dysfunctional GABA function can have really large repercussion on each of these domains. Now, we know that GABA is widely distributed in all parts of the brain, although studies have shown that it is more concentrated in some regions than in others. There are regional differences. Now, most importantly, perhaps, GABA plays a really important role in driving excitation-inhibition balance. And many theories of different clinical disorders suggest that alterations in the homeostasis of EI balance leads to clinical phenotypes. where differences in between GABA and glutamate lead to altered EI balance, which leads to differences in behavior, cognition, etc. But healthy changes in EI balance have also been associated with, for example, synchronization of cortical activity or the induction of plasticity. Given the really strong interest in GABA in clinical conditions, there's a lot of GABAergic drugs on the market. And I always say GABAergic drugs between quotation marks here, because there are a lot of drugs that don't affect GABA directly. They only affect GABA or the GABA system indirectly, but they also do a lot of other things as well. But I will get to that later. Another avenue that is gaining increasing traction is repetitive TMS. And as Professor Stagg mentioned, it can have substantial effects on GABAergic function. And TMS is being used for the treatment, for example, in depression and potentially in other disorders, but that's definitely beyond what I'm able to talk about today. Now, one thing I do want to specifically mention is that currently edited MRS is not used for any sort of diagnosis clinically. It can be used as a tool to gain a better understanding of the disease and its mechanisms, often in combination with other methods. And hopefully at some point we can use MRS of GABA to maybe predict outcome or identify specific subgroups. And I'll talk about that a little bit today as well, but we're currently not there yet. So as I said, there's a large number of conditions where GABA is thought to be altered. And in today's talk, which is only 20 to 25 minutes or so, I'm obviously not able to go into all of them in a lot of detail, or most of them at all. But in 2012, we reviewed the existing GABA MRS literature to date, including clinical work. And at that point, we found that the majority of work up to then had focused on depression and related disorders, as well as epilepsy and schizophrenia. And a lot of this seminal work came from the Yale group, who really pioneered the development and application of GABA-edited MRS in both health and the clinical conditions. Now, since then, and that's now 10 years ago, which means that I'm really quite old at this point, there's been a lot of work being done, a tremendous amount of work being done on MRS of GABA in both health and in disease. And a more recent and very thorough and extensive review was published by Schur and colleagues in 2017. And this paper really outlines the variety of studies quite well and also performed the meta-analysis to look at effects. This review did, however, focus on specific disorders, including major depressive disorder, schizophrenia, as well as autism, and there's other reviews on other conditions out there as well. So today I'm going to focus on a couple of studies because I think they can tell us some really interesting stuff more conceptually in terms of designing our studies. But first, I want to talk about where things might actually go wrong when we see it. What do we think about when we think about a GABAergic deficit? So going back to Professor Ray's presentation, the GABA system is obviously a complex one. And using MR spectroscopy, we're measuring all of the GABA within this predefined region of interest. And so when we say a GABA deficit or a GABA problem, it's not quite clear at all what we mean or whether we're able to even identify the specific GABAergic problem that we think about. And so the example slide here is just an example of part of the GABA cycle and GABA metabolism, but it does allow us to look at a couple of different places where differences in mechanism might lie. So, for example, when we see reductions in GABA measured with MR spectroscopy, it most likely reflects the availability of GABA itself through production of GABA from glutamate, potentially through glutamic acid decarboxylase, which has two isoforms, GAD65 and GAD67. Now, here the figure focuses on the synapse, but most of the GABA is actually present in the cell soma, but it is available for synaptic transmission between two interchangeable pools. So the majority of GABA, both in the soma and the synapse, is formed through GAD67, with the idea being that GAD65 kicks in when additional GABA is required, predominantly in the synapse, and then VGAD transfers GABA to the vesicles. So the problem might lie here when we're seeing changes in GABA because there's an increase or a reduction in the production of GABA. But the issue might not lie with the production of GABA. It might lie with GABA transport, either back into the neuron or into the astrocytes, or with GABA breakdown to succinic acid through GABA transaminase. And so GABA itself might be fine, but maybe it's not broken down sufficiently and there's an accumulation, or there's too much breakdown of GABA, and so you get a decrease. And finally, GABA might be affected in the GABA receptor system. That's not to say that it doesn't affect GABA production. It probably does, but the relationship is much less clear, and I'll show an example a bit later. So the GABA system might be affected presynaptically in terms of GABA as a neurotransmitter, but also postsynaptically in terms of GABA transport and breakdown, as well as receptor function. And all of these might potentially lead to quite similar phenotypes. And in, for example, autism and schizophrenia, difficulties and differences in both GABA neurotransmitter availability as well as in the GABA receptor system have all been suggested. And so this is particularly important for such heterogeneous condition. And it means that there might even be multiple underlying mechanisms that lead to similar phenotypes. So this means that when we investigate GABA function in neurological and psychiatric condition, we need to take into account that this is a complex system and that interpretation requires acknowledging that complexity in terms of we don't know where the GABA difference actually comes from. Now, MRS does allow for investigating whether GABA levels are different and altered, which might point to specific issues in neurotransmitter availability, as well as associations with functional relevance to symptoms that might provide important markers for disease. So the presence or even absence of these GABA differences does tell us something mechanistically useful, but we do need to acknowledge that the system is obviously very complex. So based on what we just learned, you might want to think about how important GAD, or glutamic acid decarboxylase, is for the production of GABA. And so what do you think would happen with the GABA levels if someone has a problem with GAD? So this is what happens in stiff person syndrome. So stiff person syndrome or stiff person disorder is characterized by muscle rigidity, spasms, and sometimes epileptic seizures. And it can be diagnosed by titrating for GAD antibodies. And about 65 to 80% of patients with this condition have antibodies against GAD, which is likely antibodies against GAD65, which attack GAD and thus lead to a lack of production of GABA. So in this study, 2DJ MRS was performed on a small sample of participants, patients, as well as controls, and GABA was measured in both cortical and in subcortical regions. And the results show that GABA in cortical regions only, not in subcortical regions, was up to 40% reduced compared to typically developing controls, likely due to inefficient GABA production. This study also shows that abnormalities in a certain specific deficit, in this case GAD65 antibodies or GAD antibodies, can be detected using MR spectroscopy and therefore may be useful for treatment and for diagnosis. Now, that said, this isn't entirely generalizable to, this is a little bit generalizable to other conditions because GAD antibodies have also been found in other conditions such as type 1 diabetes. So in the main body of my talk, I want to use different conditions to talk about considerations for doing clinical GABA MRS studies. So rather than going into all of these different conditions, I'd like to use a few examples to show important aspects of working with clinical populations. So first, I'd like to talk about my work with neurodevelopmental disorders to discuss the specificity and functional relevance of findings that we might have. Then I want to talk about the difficulty of studying heterogeneous populations and the importance of identifying your outcomes, using studies on depression as well as autism as an example. And finally, we might be able to use MRS of GABA to identify and predict clinical trajectories. And I'll use an example regarding 2 studies on schizophrenia. And after that, I'll talk a little bit about pharmacology. So I want to start with a focus on neurodevelopmental conditions, as this is my own predominant area of investigation, and it's an important one to point out some pros and cons of using MRS of GABA as a tool. So 2 years ago, when I did a version of this talk at OHBM, I showed these 3 plots, showing that GABA is altered in autism, but also in Tourette syndrome and in ADHD. And so while they're obviously very distinct disorders with their own etiologies, and there are some regional differences in GABA, these differences in GABA are not condition specific. And so it might tell us something about a specific condition, but it's not specific to that condition. You can't use it to say diagnose autism or ADHD or Tourette syndrome. And these are very heterogeneous disorders as well. Now, on top of that, in our recent work, we're not even able to reproduce these findings in larger samples. And although we do see a substantial increase in GLX in ASD, we don't see any differences in our recent studies on autism and Tourette syndrome, which are forthcoming, as well as a recent study on ADHD. But a group difference in a very heterogeneous group like autism or ADHD, is it really that interesting? It doesn't tell us much at the individual level. And so what is perhaps more important is whether there's any relevance to functional metrics. And we do see functional metrics with disorder-specific behavioral measures. Now, sadly, I can't go into too much detail, but we do see different relationships and meaningful relationships with behavior that are condition-specific. And so, for example, here we see that GLX in the sensory motor cortex in those with autism and controls correlates with a measure of clinical hypersensitivity. And so these data suggest that while there may or may not be differences at the group level, the GABA and glutamate system do play a role in maybe driving some of these clinical differences. So watch this space for more information, and hopefully these studies will be out soon. One key aspect that was also relevant to the neurodevelopmental conditions is to determine your outcome measures. There's a lot of evidence that GABA is altered in depression. And in this study, the authors studied GABA levels in the frontal cortex in youth with depression, but they subdivided this group based on whether they were anhedonic or not. Anhedonia refers to an inability to feel pleasure. they found that GABA levels were significantly lower in the group with depression and anhedonia, but not in this subgroup with depression only without anhedonia. Now, furthermore, you can see that the GABA levels on the x-axis here correlated with a anhedonia score, where patients with lower GABA levels were more anhedonic. So those participants, those patients with lower GABA were more severely affected by the condition, linking a specific subgroup of this condition to a specific symptom. And so this study shows that while we often study clinical groups, these clinical groups are very heterogeneous. And so maybe it's more relevant when we study specific aspects within these disorders, often ones that we might be able to more clearly link to the GABAergic system, that allows for delineating these subgroups with respect to neurochemistry. In addition, choosing the right symptoms or outcome measures is really important in studying these conditions as well, because they allow you to link very specific features of the condition to specific underlying mechanisms. In this wonderful but quite complex study by Roberts and colleagues, edited MRS of GABA was combined with MEG in a large sample of children with autism. And MEG was used to measure the latency of the auditory evoked response called the M50, with the idea being that the M50 response latency was modulated by GABA as well as white matter structure, and delays in the M50 response have been shown in autism before by this group and others. So in this study, a model of M50 latency with auditory radiation, fractional anisotropy, and age as independent variables was able to predict 52% of the M50 latency variance in typically developing children, but only about 12% of the variance in the children with autism. So this model was then used to identify a subpopulation of those with ASD that were outside significant outliers to the TDE model. So they were outside 85% confidence interval. What they showed is that this ASD outlier group that they found exhibited unexpectedly long M50 latencies in conjunction with significantly lower GABA levels. And so here in this study, it's a great example of starting to look at stratification, where a smaller subgroup of a heterogeneous population exhibits different responses and different GABA levels. And so perhaps reduced GABA can be predictive of a specific subphenotype of a very heterogeneous condition. GABA and glutamate have also been a strong topic of investigation in schizophrenia, and a variety of theories point to deficits in both excitatory and inhibitory neurotransmitter in this condition. So for example, glutamate excitotoxicity might lead to neuronal damage, it might lead to cognitive deficits, and abnormal glutamate receptors on inhibitory interneurons might lead to inefficient GABA function and to hyperdopaminergic and glutamatergic function. In addition, GAD67 has been suggested to be affected in schizophrenia as well. So in this study, Laura Rowland and colleagues performed one of the largest schizophrenia studies to date, and they separated them out in between older and younger cohorts with schizophrenia. And the findings show that normal ACC levels are present in those younger patients with schizophrenia, but decreased ACC GABA levels are present in older patients. A linear regression showed an increased decline in GABA levels with age compared to healthy controls. And also those participants with higher GABA levels had better working memory. And so this study is really relevant and important for a few key reasons. First of all, they used a large cohort, and I'll discuss this later, but many clinical studies suffer from low ends. In addition, they used a macromolecular suppressed sequence, but they replicated their previous findings of reduced ACC GABA with GABA+. And they show a difference in the age trajectory, which is really relevant to disease progression. We know that early in a condition, you might not see differences, but later you might. And this allows for studying dynamic or longitudinal changes in GABA as an indicator of disease progression. What might be even more important is to study whether a disease can be predicted before symptoms arise. Early diagnosis may really support early intervention as well as better outcome. So Modinos and colleagues studied subjects at ultra high risk for psychosis, which was assessed using the community assessment of at-risk mental states. Here they studied the medial prefrontal cortex, given its involvement in the emergence of psychosis, and they measured this in 20 patients and 20 controls. Well, they didn't find any difference in the GABA levels between groups per se, which is consistent with the previous slide. They found a relationship between frontal GABA and the negative symptoms from this inventory, but not positive symptoms, suggesting that those participants with higher GABA levels had fewer prodromal symptoms for developing psychosis. And this kind of investigation, even though it was done in a small sample, allows for early assessment of early markers of a condition, which may potentially influence early diagnosis or early intervention. So this is also really important and shows a really useful role for GABA MRS. For additional reviews, I would look at these two papers, one by Gerard Dreyer and one by Jeroen de Jonge, which are wonderful reviews on this topic. Now, in the last portion of my talk, I want to briefly talk about pharmacology and then about some limitations. So in one of the first studies to use MRS to study GABA, the effect of gabapentin on GABA levels was studied. And gabapentin can be used in the treatment of epilepsy, migraines, as well as anxiety disorder, as well as others. So gabapentin mimics the action of GABA, but is not a GABA agonist. It doesn't actually affect the GABA receptors, but rather binds to calcium channels directly. So in this study, gabapentin was given to epilepsy patients in 2 separate doses compared to those taking other epilepsy drugs. And GABA levels were shown to be higher with about 50% in those patients on high doses. Sequential measures before and after gabapentin showed increases in GABA as well. But some abnormalities in the GABA system allow for abnormal pharmacodynamics. So in another study, benzodiazepines, in this case clonazepam, was given to patients with panic disorder, which has been linked to abnormal GAD65 expression, as well as control participants. So benzos increase the efficacy of GABAergic function and they bind to very specific GABA-A receptors. So at baseline, you can see that those with panic disorder showed reduced GABA levels compared to the control group. Now, at treatment, those with panic disorder, in control patients, occipital GABA levels decreased, as you can see here, suggesting that benzodiazepines maybe suppress GAD activity. However, there was no response in patients, as you can see here, suggesting perhaps an insensitivity to drugs. And this is really important because it shows that when a system is dysfunctional, in this case, for example, the GAD and GABA production, a drug's normal action is not appropriate. And so we want to understand why some people do and do not respond to drugs, which is really important in treatments of different disorders, where MRS can actually be a really useful contributor. So one limitation here is that the long-term effects of benzo use aren't well known, but they are seeing that people who might have a GABA deficit don't respond to a drug affecting the GABA system. And similar effects have recently been shown in published and unpublished work with respect to arbaclofen and riluzole cannabinoids in autism spectrum disorder, where those with autism, where an EI balance difference is suggested, do not respond the same way as the control group. And that makes sense. If the system is working different, something affecting that system, the drug, might also work differently. In this study, they use vigabatrin, and vigabatrin is a GABA aminotransaminase blocker. So it blocks the breakdown of GABA. And so in this study, vigabatrin was given to patients with epilepsy and GABA was measured serially. And this figure here shows the dose response information. So GABA levels increased due to accumulation, increasing with up to 60 milligrams per kilogram. In addition, clinically, the number of seizures went down. However, there are also conditions where accumulation of GABA is the actual pathology, where that's a problem. So in a condition called semialdehyde dehydrogenase deficiency, means that GABA cannot be catabolized from succinic semialdehyde to succinic acid, leading to an accumulation of GABA. And so you see an accumulation of GABA in the brain. Moreover, when that happens, GABA starts being broken down into GHB instead through semialdehyde reductase. And so GHB is more commonly known as the day-drug drug or liquid E, and you do not want that in your system. Now, this condition is rare. It is characterized by developmental delays, seizures, ataxia, as well as cognitive dysfunction. And in this case study, they performed unedited MRS, which should be noted, in a patient with this deficiency. And they showed very large accumulations of GABA, about 1.5 times as much in the patient, particularly in the gray matter regions compared to the controls. And so what they also showed an increase in GHB. So these studies show that specific abnormalities in the GABA system are detectable using MRS, and that we can also target drug treatment and the effect of drug treatment in certain studies, although there's also plenty of studies out there that don't show any differences with the application of drugs affecting the GABA system, either directly or indirectly. So there are obviously some limitations when we're studying clinical conditions, and we need to be aware of these different limitations. So the first one is scan quality and motion. Studying clinical groups, particularly those who have intellectual disability or other cognitive difficulties, is difficult, and putting them in the scanner for a long amount of time, which is what MRS takes, is not always feasible. And so sometimes you have populations who have a lot of attrition, who move a lot more, and so therefore affecting data quality. And so when we're doing our analysis, particularly with clinical groups or with pediatric groups, we need to make sure that any differences or correlations we find are not due to differences in the behavior in the scanner, methodological differences, including scan quality and motion. And so it's really important to report these things and test for these things first. Secondly, recruiting clinical populations can be quite difficult. And so what you often see with clinical studies is that they suffer from smaller sample sizes. And so the generalizability of these studies is not always obvious. And so you can see this in the SURE review, as well as a wonderful review on autism by Laura Iram and colleagues. And so these small sample sizes are difficult. And so we need to go to bigger sample sizes to see whether these data are reproducible. And like I said, we've not been able to reproduce our prior findings. And this is partly because these conditions are very heterogeneous, but it might partly also be simply because we don't have the power to detect these differences in small sample size. And so this is where we need to move towards larger sample sizes, and we might have to start doing more multi-site studies or big cohort studies as well. Now, furthermore, when you look at the literature, you see a lot of differences in study design. People have used different field strengths and different pulse sequences that might also lead to an inability to reproduce some of these findings. Studies, sadly, still often use small voxel size and therefore low SNR. And so those data might be more difficult to interpret. And of course, it really depends on where you're studying and who you're studying. As there is a lot of variability in the regions that are studied, there might be regional differences, and there might be differences in the different cohorts that you study as well, whether they're more intellectually disabled or whether they're coming from a specific region, etc., what the education level is, those sort of things. So keep those things in mind as well. And finally, people have also studied other edited metabolites of interest beyond GABA that are part of the GABA system, including glutamate, glutathione, NAG, etc., that are all part of glutamate metabolism. So that is also really important to keep in mind when you're doing this. And increasingly, we're starting to look at interactions between metabolites as a measure of, say, altered glutamate metabolism that I sadly don't have time to talk about today. So to summarize, GABA levels might be altered depending on the condition that we're studying, and we need to often have a good mechanistic basis of looking at this. Studies have shown that GABA can be related to psychiatric and clinical symptoms, as well as behavior and cognition. We showed this in autism, people have shown this depression and in schizophrenia. And this is probably more relevant than group studies where we're looking at simple group differences because they don't tell us at the individual level, which is where we need to come towards. But we need to make sure we choose our outcomes very carefully. We also discussed important differences to consider when we're interpreting our findings in terms of where the differences lie. Is it in synthesis, metabolism, in neurotransmission, or in interneuron pathology? Look at the available literature out there and think about where things might go wrong and whether you're expecting a difference in GABA, yes or no, or whether you're expecting GABA to affect people clinically. And finally, we need to take into account study design, sample size, medication, heterogeneity, field strength, reference compound, and scan quality when we're doing these studies. Most importantly, they need to be reported. And increasingly, people are focusing on reporting guidelines and quality assurance guidelines, including the recent consensus MRS and MRS paper, as well as the MRS quality assurance tool that I developed with Amy Peake. So have a look at them when you're starting to write your papers or even plan your studies in terms of what information is important. With that, I thank you very much, and I'm excited for the live session, and I'll gladly take your questions there. So thank you.